ahead with whatever numbers we have. I think it's fine.
Yes, I think we should go ahead. It's almost 3 p.m.
Yeah, yeah. Okay.
So, a very good afternoon, dear Principal Sir, Professor Shastri, Professor Prajval Shastri, Professor Deepa Khushalani, Professor Lakshmi Ravishankar, our Head of Department, Marazban Sir, and our presenters for the day, Asma Jaisal, Anu Jithin, and Srinath, and everyone in the audience. A very, very warm welcome to all of you. We are gathered here today for the webinar. As you all know, Inclusion, a cornerstone of scientific progress. The star event of ALCHEMIA 2021, the annual intercollegiate fest of the Xavier Association of Chemistry. We are greatly fortunate today to have with us stalwarts as Professor Prajval Shastri and Professor Deepa Khushalani. Also, we are delighted to have you all in the audience with us. It tells us that, if anything, the thought of inclusion is one all of us deeply care for. A lot of activities recently globally have been quite detrimental to gender parity and inclusion broadly. So I think this webinar is quite well timed to discuss these questions and revisit our thoughts on this issue. And having so much support indeed gives us hope. So in addition to our eminent speakers and enthusiastic presenters of the day, the small ventures of ours would not have been possible without Professor Lakshmi Ravishankar's kind and continued guidance, the efforts of ZAC's faculty in charge, Professor Ashma Agarwal, and the cooperation of all ZAC members. Xavier's, I am proud to say, is an institution that has always given a special emphasis on inclusion, and perhaps it is befitting and quite high time that we of the Xavier's Association of Chemistry had a gathering to discuss this question. We are really fortunate today to have with us our principal, sir, Dr. Rajendra Shinde, who could take time out of his really busy schedule to come and grace our event. I would request sir now to bless us all with a few words. Principal, sir.
Thank you, Bonabiti. Have I pronounced your name correctly?
Yes, yes.
Yes, thank you for highlighting one of our core values, inclusion. So good evening or good afternoon and welcome to this webinar on inclusion, a cornerstone of scientific progress, organized by ZAC, Xavier's Association of Chemistry. On behalf of the management and the college, I welcome our speakers, Professor Prajval Shastri and Professor Deepa Khushalani, to this 152 years old iconic institution, though we are talking virtually, founded by Society of Jesuits. True to its vision and its key values, innovation, integration, and inclusion, the college always tried to inculcate these principles in our young students' mind. I just want to highlight a couple of achievements of St. Xavier's College, though they are well known. St. Xavier's College is an autonomous institution since 2010, affiliated to the University of Mumbai from its very establishment in 1869. So, thus completing 152 years in January 2021. We have been NAC re-accredited 3 times, and all 3 times we have scored top grades. Last 4 consecutive years, we were the only college from Mumbai to acquire a spot in the list of top 100 colleges in National Institutional Ranking Framework. Twice, we have been awarded the College of Potential of Excellence Award and a College of Excellence Award once in 2014 by UGC. In addition to the Best College of University of Mumbai, DST FIS DBT star status of our science departments are just a few accolades to mention here. Our contribution to education and research is not just recognized and acknowledged by RUSA Maharashtra, but also by the Department of Biotechnology, Delhi. We were awarded DBT Builder grant of 3 crores for our interdisciplinary postgraduate research. Today's theme of the webinar is very apt and in sync with the ethos of the college, and this assumes the significance as our chemistry department will be the first science department in the college, and I guess probably in the University of Mumbai. Next year, we would be producing a visually challenged graduate in chemistry. A good example of inclusion. At present, we have more than 100 students with special needs, and we have been providing them various accommodations in their teaching, learning, and evaluation methods. It is a matter of great pride that our distinguished women alumni in these 152 years have significantly contributed to the development of our nation and left their mark in the history. Just to emphasize the point of inclusion, I would like to remember a few women scientists, especially here, who are our alumni. Dr. Shubha Tole, Dr. Vidita Vaidya from TIFR, Dr. Swati Patankar, Dr. Janvi Punekar from IIT Bombay, the former director of NIV, Dr. Khurshid Pawri, Dr. Pia Nagraj from NCL Innovation Park, Dr. Rich Ricky from IISER Pune and Arundhati Ghatak from IISER Bhopal, Dr. Reni Bojes from Indian Institute of Science, Bangalore, Dr. Antara Banerjee, a recent young scientist from National Institute for Research in Reproductive Health, a young physicist, Dr. Amrita Gadge from Sussex University, Dr. Swati Piramal, who is a scientist turned into an industrialist, and many more. The list is quite a long list, but these are just few to mention here. So one can see how the practicing of our core value, inclusion, has resulted into a very significant contribution, not only to the nation, but to the global community, and will continue to do so. I welcome all of you once again for this webinar on inclusion, a cornerstone of scientific progress. Thank you, Bonabina.
Thank you so much, sir, for your kind and wise words. Indeed, these are times one feels so proud to be a Xavierite. So, before proceeding, I would like to mention one thing, that after the first 3 sessions of this webinar, we shall have an elaborate discussion and question answer session. So, we will be only too glad to hear from the audience then. Either you type it in the chat box, or you may use the raise hand button and unmute yourself. Putting on your video while speaking is also desirable. It is a sincere request to one and all to participate actively in today's discussion session, because what is inclusion after all, if not more voices heard and more stories shared? So, without further ado, let me hand over to Bhavika to introduce to you our very first speaker and one of the distinguished guests of the day, Professor Prajval Shastri. Over to you, Bhavika.
Now, let me introduce to you our first speaker and one of the distinguished guests of the day, Professor Prajval Shastri. Professor Shastri has been an astrophysicist of over 35 years. She got her PhD from the Tata Institute of Fundamental Research and held postdoctoral research positions in the University of Texas at Austin, University of California at Berkeley, and the Harvard-Smithsonian Center for the Astrophysics before joining the Indian Institute of Astrophysics, where she was a faculty for 23 years. In her research, she specializes in the empirical investigation of giant black holes that are found in the centers of distant galaxies. She uses telescopes operating at radio, infrared, optical, UV, X-ray, and gamma ray frequencies to study these distant galaxies and their central black holes, and in particular, the consequences of jets launched from their environment at relativistic speeds and the impact on star formation in their host galaxies. She has been a Fulbright Senior Fellow at Stanford University, Senior Associate at the International Center for Theoretical Sciences, TIFR, a distinguished visiting fellow at the Australian National University, and is currently adjunct professor at the International Center for Radio Astronomy Research, Australia. She's extremely passionate about science outreach, believes that cultivation of scientific thinking is for everyone, uses astrophysics as a vehicle to engage lay audiences of all ages with these questions, and has led several national campaigns in this context. She's also deeply concerned about the gender disparity in the sciences. She was the country team leader of the delegation of Indian physicists to the international conferences on women in physics and is a member of the Women in Physics Working Group of the International Union of Pure and Applied Physics. She's founder and past chair of the Gender in Physics Working Group of the Indian Physics Association and a member of Working Group for the Gender Equity of the Astronomical Society of India. In addition to her research publications, her published work includes popular articles on astrophysics and on the subject of science and society. Now, without taking any more of your time, I would like to invite Professor Shastri to begin.
Hi, can you hear me?
Yes, ma'am.
Okay. Good afternoon, everybody, and thank you very much for this invitation. This is a particularly special invitation and therefore also a little bit of regret because when I was studying my master's in IIT Bombay many decades ago, Xavier's used to be a favorite hangout place. So I really regret not being able to do it in person, but it is really special for me to speak to all of you today. I will try to share my screen now. Will I be able to share just my window?
You should be able to, I think.
Okay. It's not allowing me. Okay, let me try again. Okay.
You just now stopped sharing the screen. Earlier it was...
Yeah. I'm just going to try once again.
Okay.
Can you see my screen now?
Yes, ma'am.
Hello?
Yeah, we can.
Okay. And can you see my cursor as it moves around in the screen?
Yes.
Okay. So now I'll go to my next slide. And if you don't see the next slide, please tell me. Okay. So this is my title. And so I want to begin by telling you how astrophysicists study the cosmos. So we study the cosmos using the whole of the electromagnetic spectrum. We also look at neutrinos which come from the cosmos. And not only that, in more recent times, we have been able to listen, in a sense, to the ripples in the fabric of space-time, meaning gravitational waves. So these are the this is the whole range of things we use to study the cosmos. And so when it comes to the electromagnetic spectrum, facilities with telescopes that look at visible light are located on Earth. Also, telescopes that look at radio frequencies are located on Earth. However, because the atmosphere is not transparent to the whole electromagnetic spectrum, in particular to ultraviolet, X-rays, and also gamma rays, even infrared, such telescopes need to be launched out into space. And this is showing you a plot of the atmospheric transparency as a function of frequency. And so you can see that visible light and radio light come through, whereas infrared, X-ray, ultraviolet, etc. do not. And so for those, we need to put the telescopes out into space, and these are some examples of those. Spitzer and Chandra by NASA, and AstroSat by the Indian astrophysics community and ISRO. These are examples of neutrino observatories, which I mentioned earlier, and this is one component of the gravitational wave observatory. So now that I've told you that we look at all kinds of frequencies, how do we render our data? So when it is visible light, we can just make an image and we understand what that is. But what if it's an image in, say, the infrared or at radio frequencies? How do we render that? So there are many different ways to do it. But one very popular and effective way is what we call false color picture. So I'll just explain what that is. So here is a picture of a cat as we would normally take it. And this, I'm claiming, is an infrared picture of a cat. So it shows how much infrared is coming. We know that, cats' noses are cold and their eyes are warm and so on. So you would expect more infrared radiation from the eyes and less infrared radiation from the nose. So what a false color picture is the colors depict how much intensity is coming. So that's why we call it false color, because the colors don't represent the colors themselves. They represent how much light is coming at a particular intensity. So this is a false color picture, and it makes sense. This is also a false color picture of a cat again, and it is very similar, except that a different set of colors is being used to render it. So false color pictures, in false color pictures, the colors are arbitrary. They're completely determined by the renderer, and therefore a false color picture makes sense only if accompanied by a key like this, which tells you which color is what intensity. And so the colors are arbitrary. So here is the same data represented by in another way with a different set of colors, but they are representing the same thing because the key tells you that they are representing the same thing. Now, this is an example of an image of the planet Uranus, and both of these are the same image. The one on the left is a true color picture, meaning it is rendered in a way that the human eye would see. And the one on the right is a false color picture of the same thing. So I will be showing you a lot of false color pictures. So here is an example of an actual astrophysical object, a galaxy, which is famous as the Sombrero Galaxy because it has this shape. And so here is the visible light picture. In other words, it's a picture that if we had very, very sharp eyes, we would see it this way. And this is the same image except represented or rendered as a false color picture. So the color just represents the intensity, and this is by the Hubble Space Telescope. And the same galaxy imaged in X-ray light looks very different, as you can see. So here you're mostly seeing the stars, whereas here you're seeing other things which don't emit visible light necessarily, but emit X-ray light, and this was taken by the Chandra X-ray Observatory. And this is an infrared image of the same thing. So what you see as a dark band here, which is actually due to the dust particles between the stars, is coming out very prominently in this infrared picture, which was taken by the Spitzer telescope. And this is a picture where all of these are overlaid one on top of the other. So this is another example of a real cosmic object rendered as a false color image. Now, another thing astrophysicists use a lot is spectroscopy. So of course, all of you, I'm sure, are familiar with spectroscopy, and you all know that if you have, for example, a hot black body and you take a spectrum of it, it will look like this. You will see a continuum spectrum, a rainbow. If you have a cloud of gas, either in the laboratory or in the cosmos, and you light it up with a hot, let's say, black body. And if you look at the cloud of gas directly, you will see emission lines like this from the cloud of gas, which are signatures of the atoms in the cloud of gas. On the other hand, if you look at the cloud of gas, if you look at the background source through the cloud of gas, you know that you will see the spectrum of the background source as a rainbow, the same spectrum, and the same atomic lines, but seen in absorption as black lines, because the cloud of gas is in front of a much hotter body. This is very familiar. You also know that the spectral lines are fingerprints of the atoms, and so, for example, carbon would give this pattern of lines, oxygen would give this, and so on, and we know all this very well from our laboratory experiments. And this is another way of representing the emission lines, and this is another way of representing the absorption line. Now, spectroscopy is a very, very powerful tool for astrophysicists. You might think, oh yeah, of course, you will get to know what the composition of what you're looking at is, and that is true. But there is a couple of other things which I will get to in a second. So I just wanted to mention that my slides got a little disordered, but I wanted to mention that astrophysicists tend not to use kilograms and watts and so on as units, because they're too small for our purpose and there would be too many zeros. So we tend to use the mass of the sun as a unit of mass, so we will refer to something as so many solar masses, and similarly we tend to use the luminosity of the sun as a unit of luminosity, and we will refer to something as 1,000 solar luminosity or something like that. So to come back to the issue of the spectra, so not only can we get the composition, because when a source moves with respect to us in our line of sight, the lines will get shifted because of the Doppler effect. From the spectrum, we can also infer the speed of the object in the line of sight. So it becomes a much more powerful tool than just deciding on the composition. Not only that, the kind of emission lines that we see depends, suppose you have a cloud of gas, for example, the kind of emission line we see depends on the temperature of the gas, not just the composition. And so by looking at the spectra, we can infer temperatures and densities. So there's a huge amount of physics that can be inferred just by doing spectroscopy. So spectroscopy is an extremely powerful tool for astrophysicists. Okay, so now let us ask the question, what are black holes? So black holes are chunks of space-time from which even light does not escape. I think many of you know this already. And so is there an intuitive way of understanding that? But before that, I should tell you what I mean by space-time. So space-time, it's just a fancy way of saying that spatial coordinates and time coordinates are very closely linked. So for example, you know this typical way of representing three-dimensional space, and suppose you have an ant there, then you will say that the spatial coordinates are represented by these three coordinates. However, it is not a complete description. So for example, if I say that I'm in the southwest corner of the city of Bengaluru, that's not a complete description. I should say I'm in the southwest corner of Bengaluru now, because I may not have been here last week because I was traveling or something, right? So similarly here, and so that is why you have this notion of space-time. And so if this ant moved in position, you could say that, you could draw a different diagram and say that the ant is now here, and so that is one way of showing how the ant is moving in space-time. And we tend to use these plots which we call trajectories, where we plot time on the x-axis and the spatial movement on the y or z-axis. Right? But typically when people talk about space-time and what happens to things in space-time, then they again suppress one spatial dimension compared to this triaxial thing. But one has the time axis on the vertical, unlike in the trajectory case. So then you have these two as the spatial axes and the vertical axis as the time axis, and then you show the movement of something that way. And so here time is vertical. That's just something to remember. Now, what does it mean that you have a thing called a black hole that from which even light cannot escape? So let's look at the word escape, and let's try to recall what we learned in high school about escape velocity. So we all learned that, you throw something, we didn't necessarily learn this in high school, we learned it much earlier, that if you throw something, it's going to fall back to the ground. And if you throw it a bit faster, it will travel a bit further, but it will still fall back to the ground. And then in high school, we learned that if you throw something really fast, for the Earth, and at the surface of the Earth is about 11 kilometers a second, then this thing would get launched into outer space. And so we call that the escape velocity, which is about 11 kilometers per second. So for the moon, the escape velocity is lower. It's about 2 kilometers a second. Now, we know the formula, we learned that in school for this escape velocity, and it depends on the mass of the thing we are trying to escape from, and it also depends on how far we are from the center of that mass, right? So these two factors determine the escape velocity. So that is crucial. Now imagine what happens if you squeeze this Earth. So you keep the same mass of the Earth, but squeeze all of it into a smaller size. Then what happens? Then this value goes down, and so the escape velocity increases, right? So now, suppose you set the escape velocity to be the velocity of light, which is 300,000 kilometers a second. Then what you get is a relationship between this term r, which is basically the distance between the center of the mass and the surface, and the mass itself. So you get this relationship. And if this relationship is satisfied, then even light cannot escape from it, and in other words, it becomes a black hole. So it turns out that if you do this math, it turns out that you have to squeeze all of the Earth's mass into a marble size in order for the escape velocity to be the velocity of light, and therefore for it to become a black hole. Now, this was an idea that came very, very early to people. There are documented records of this by a priest scholar called John Mitchell in 1783 and Pierre Simon Laplace in 1796 and so on. And even they realized that when you squeeze the Earth, for example, you need to squeeze it to marble size. So that is like an unimaginable, unphysical density. So they realized that things that will make the escape velocity equal to the velocity of light have to be very, very big. In other words, they have to be cosmic. But they were dark, right? I mean, these were just ideas, but it was clear that these objects would be dark because escape velocity is equal to the velocity of light, so no light is coming. So then how do we see them? We won't see them, right? They did speculate about how we might be able to see them if they are sort of bound to another object and so on, but there was no progress in that direction, and no such objects were seen. Now let's fast forward to 1915, when Einstein proposed his general theory of relativity, and this was a very revolutionary idea, and it was a completely different way of looking at gravity. So this was a way that you no longer looked at gravity as a force, but you looked at it as something else. So Einstein thought about this whole scaffolding, this whole space-time in which we all are, as fundamental and as masses curving this space-time. So that is how he understood gravity. So for example, that is depicted here in this picture. Of course, here space-time is really 3 dimensions of space and 1 dimension of time, which is hard for us to imagine on a piece of paper. And so typically we suppress the one spatial dimension and show it this way. So this is showing you a 2-dimensional space-time fabric. And what happens if you put a mass somewhere there? That the idea is that it will curve the space-time. So this was a new way of looking at gravity, which is what is shown in this diagram here, which is again a coordinate system. So John Wheeler articulated this very beautifully. He said, Einstein's theory of general relativity says that mass tells space-time how to curve and space-time tells mass how to move. So now, what happened then? So the same year that Einstein proposed this theory, Karl Schwarzschild, who was a physicist professor but who went to serve in the German army, found a solution. Within months, he found a solution or a consequence to Einstein's theory, and he came up with this formula. But the intriguing thing was that this formula was exactly the same as the formula that I came up with, I showed you earlier with that game that we played by setting the escape velocity to the velocity of light. So did that mean that this was a black hole? Let us go back to the idea that masses curve space-time. Okay, so now if masses curve space-time, we know that light travels along the shortest distance between 2 points. And in our everyday experience, therefore, it always travels in straight lines because the shortest distance between 2 points is along the straight line. But suppose you have a mass and that is bending space-time. That means that the shortest distance between 2 points will be not straight lines anymore, but will be bent, right? So therefore, masses must bend light. This was a prediction of Einstein's theory of general relativity, and a physicist called Arthur Eddington thought of testing it. The point is that all masses, according to this theory, will curve space-time, meaning my laptop's mass, my mass, Xavier's college building's mass, everything will curve space-time. But space-time is a very stiff thing, so it's not easy to significantly curve it. So therefore the curvature that results because of all these things is very minuscule, and it's not certainly measurable with the capability we have now. However, what was realized was that during a total solar eclipse, if one were to look at a star which is close to the sun in direction, without the eclipse, the star's light would directly reach the earth. But if one were to look at it during an eclipse, when the light from the sun is being obscured, and so therefore you can see the stars near the sun visibly during the day, you would expect that the position of that star would shift because the light would get bent by the mass of the sun. Now the sun has a lot of mass, so you would think that would significantly bend light, and therefore you would be able to measure it. And sure enough, Arthur Eddington did measure the bending of light, and this was a demonstration in favor of Einstein's theory of general relativity. Today, of course, the bending of light is part of our everyday experience because we have GPS, and clocks will tick slower on Earth as seen by the GPS satellite, and therefore we need to correct the signals from the GPS satellite for this effect. But at the time, what happened was, even though Eddington confirmed the bending of light at the solar eclipse, and even though the other prediction of general theory of relativity, which was the precession of the orbit of Mercury, was also confirmed, there was a lot of skepticism about this solution that Karl Schwarzschild had found where it was similar to the idea of which came from classical theory and equating the escape velocity to the velocity of light, because it implied infinite curvature. In other words, it's people call it a singularity. It implied a singularity, which means things go infinite. And that is something that people don't like. Singularities are extremely uncomfortable. And so there was a lot of skepticism about this formula and whether indeed it meant anything. So it wasn't forgotten, and along the way there was a lot of work. For example, Subramaniam Chandrasekhar showed that anything that is roughly the mass of our sun, when its fuel is all finished, will collapse into something we call a white dwarf, because the what we call the electron degeneracy pressure, which you, I think, as chemistry students are familiar with, will hold up all that mass of the star even though its fuel is all finished. However, if it is larger than that mass, then this pressure will not be able to hold that up, and he did say one is left with speculating on other possibilities. And then in 1939, Robert Oppenheimer of the atomic bomb fame investigated the problem, and he found that stars could collapse into something with infinite curvature. And they argued that a star at collapse will close itself off from any communication with a distant observer, and therefore as someone outside of this closed off surface will only sense the gravity and nothing else. And so that would be sort of like a black hole, but there were still many questions. There was still a lot of skepticism, even by Einstein himself, as to whether these objects could be real. Was it an artifact of the mathematics, and would the matter eventually just come out? Or could deviation from some symmetry prevent this collapse into such a singularity? Or could quantum physical effects prevent the collapse, and so on? So now fast forward to the early 60s, and a very strange object was found in the cosmos. This was called 3C273. The name is not important, but the thing is that it looked like a pinpoint of light, just like all the other stars in the sky. So here you can see this pinpoint, and it looks like everything else. However, when a spectrum was taken of this object, this is a spectrum of a typical star. So you would see this black body continuum, and you would see the absorption lines as black lines, just like we see the Fraunhofer lines from the sun. However, that was not what the spectrum of this thing looked like. This is a spectrum of what most stars look like. This had an emission line spectrum. Not only that, the emission lines were not recognizable. And so it took the genius of somebody called Martin Schmidt, who was an astrophysicist, to realize that the reason we were not recognizing these emission lines was that they were shifted by a very large amount, by 16%. From their laboratory values. And so once he realized that, then all the lines fell into place and everything was recognizable, Balmer lines, oxygen, so on. What did this mean? This meant that the shift in the lines was not just a Doppler shift, but it was due to the expansion of the new universe and the stretching of space-time. And so therefore it meant that this object was extremely far. And if it is that extremely far and it still shines as bright as a star within our Milky Way, then it meant that this object was enormously luminous. In fact, unexplainably luminous, because it was as luminous as all the stars of the Milky Way or any other galaxy we knew put together. And so George Gamow wrote this poem even, which said, "Twinkle, twinkle, crazy star, biggest puzzle from afar. How unlike the other ones, brighter than a billion suns. Twinkle, twinkle, crazy star, how I wonder what you are." So there is another very interesting argument which they made in order to, which just sort of deepened the mystery. So as it was extremely hard to explain this extremely large luminosity, right? More than 1 billion suns. So it couldn't be explained by a whole bunch of stars together or exploding stars or anything like that. But what made it worse was that this pinpoint of light was seen to change on time scales of days. Now, astrophysicists have one very interesting tool in their toolkit, and that is called the light travel time argument. So I'll just explain that very quickly. So if you have in this diagram time going towards the right, and you have this gray circle which represents a hypothetical cosmic object, and let us say it instantaneously brightens right after some time. So this represents this brightened object. The same object instantaneously brightens. We won't get into why and how and so on. Just imagine that it instantaneously brightens. Now the point is that we are observing it from a very far distance, and we will therefore see the photons from the front surface reach us before the photons from the back surface, and the photons from in between will come in between. So if this thing instantaneously brightens, we watching it from here will not see an instantaneous brightening. Instead, we will see the front photons first brighten, then the next ones, and then the next ones, and then the final photons. So we will see the brightening spread across some time interval. And how much time interval? The amount of time that light takes to travel this length. So you can spin the argument around and say that if you see a change in the amount of light that is coming from a cosmic object, then that object cannot be bigger than the distance light can travel in that amount of time. So therefore, using the time argument, you can come to conclusions about how big this object is. Remember, we're just seeing a pinpoint, so we cannot measure how big it is in the sky even. But we're just, from the pinpoint, we see a change, we see the light change, and therefore we are able to infer how big it is. And it turned out that this object, particularly this 3C273, was changing on even time scales of days, which meant that it must be smaller. Whatever is producing this enormous luminosity of 1 billion suns had to be smaller than roughly the size of our solar system. So that was impossible. So the only way was to postulate the kind of objects that Oppenheimer talked about, and Salpeter and Zeldovich and Novikov came up with this idea that if you have such an enormously gravitationally strong object, then you can harness the gravitational potential when matter reaches very close to it. And so then this matter will be attracted and swirl around it and plunge into the hole, but in the process will get accelerated, heated, and therefore shine very, very powerfully, and therefore we will be able to see it from very vast distances, and they could account for the kind of luminosity that this strange object called 3C273 showed. But still, the questions remained. I mean, how can these objects really be real? And was it an artifact? And so on and so forth. And then came along a few years later, Roger Penrose, who had the answer. So he looked at the same problem again, the problem that Oppenheimer had looked at earlier about a star collapsing. He applied extremely innovative topological methods. He was trained as a geometrist, and he had this enormous geometric intuition into how space-time can behave. And this is the diagram he drew in that paper. I really love this diagram, so that's why I'm showing it here all in color. Of course, his is a very simple pencil drawing. And he also found that Oppenheimer's solution was correct even without any kind of very stringent assumptions. So it was realistic to expect that to happen. And although he too found a singularity, It's not that he didn't find a singularity, meaning it's not that he didn't find infinite curvature, but he found that this surface would act as a shield, and the infinite curvature would be in the very center. So in other words, once you cross this surface, whose radius was derived earlier by Karl Schwarzschild, and before that I showed you the escape velocity formula and so on, but it would shield this central point. Once you cross the sphere, all directions lead into the future. All directions lead into the end of time, so to speak, and it is a sphere of no return. But it will behave exactly like saltpeter and Zeldovich and Nalkov required. So now, that's why people were more comfortable. So as long as you didn't ask questions about what happened inside the sphere, you could still argue and calculate about what happened outside it. And so then that was the accepted explanation for these objects, and these are more and more examples of it which emerged over the decades. So these are now false color pictures, and what this shows you is a visible light picture of a piece of sky where you see a lot of stars and galaxies, and this in particular is a galaxy of stars, and from its center you can see these two sort of jet-like structures emerging and then diffusing out into intergalactic space. That is a radio picture, and so this is showing us radio emission from this plasma that is being squirted out from the center of the galaxy out into intergalactic space. This is another example of the same thing. Again, two false color pictures. In blue is a visible light picture, in red and yellow is a radio light picture, and that is showing you the same thing, that from the center of a galaxy are squirted out these two jets of plasma reaching out into intergalactic space. Here are more examples. However, this is still circumstantial evidence for the existence of a black hole. We know that things are coming out. You might ask, how do you know it's coming out? How do you know that it's not coming in from these two big blob-like things? And that is what this data is showing you. These are images taken at in radio frequencies, but at different epochs. So you take an image, then wait, take another image, and so on, and the date is shown at the top right corner, and then you put them all together to make an animation, and you can see, right, that things are actually moving over here. So we know that stuff is coming out from the center and going into intergalactic space. And this is a computer simulation which incorporates all of this around a black hole. That is all the physics we know around a black hole, where you have stuff coming in very close to a black hole. It gets sucked in, it swirls around, it gets heated, it becomes plasma, it generates magnetic fields. So these green lines represent the magnetic field lines, and then in the process launches plasma in two directions, which get squirted out and get launched into intergalactic space. So these are not real data, but this is a computer simulation knowing the best physics that we know, general relativistic magnetohydrodynamics. So that has been put into this, and it shows you, what it is showing you, that it is possible that if you have a black hole, general relativistic effects will dominate, and if you have material that comes very close to it, you could possibly generate the kind of structures that we see. Also, this is an example from my own work, where in this galaxy we found not just one, but actually two of such, we call them accreting giant black holes, that is with stuff coming around and swirling into it, which this is a visible light picture, this is a radio light picture, an X-ray light picture. They all show that these two things brighten up because of this phenomenon. But still, it is only circumstantial evidence, as in we see these structures, we see this enormous power, we see these plasma jets squirted out into intergalactic space, and the only explanation we have is to say that there is a giant black hole in the center of the galaxy. So it's a Sherlock Holmes argument saying that when you've eliminated the impossible, then whatever remains, however improbable, must be the truth. So what would be direct evidence? Direct evidence would be, for the black hole, would be dynamical, meaning you actually see something driven by the gravity in, say, Keplerian orbits. Now, the best candidate to find that was our own galaxy. And the center of our own galaxy. So this is a picture of the Milky Way. I hope all of you have seen the Milky Way for real sometime in your lives. This is taken from Leh by a friend. And in fact, Galileo Galilei himself, when he turned the telescope at the Milky Way, he had realized that we see the Milky Way as patches of light in the sky simply because there are zillions of stars in there. And that's why we see them as patches of light. Now, you may not be familiar with the Sagittarius teapot, especially the amateur astronomers among you. And near the spout of the teapot is where the center of the Milky Way is. So as you know, the Milky Way we know is sort of a spiral shaped structure. And so the very heart of it is in this direction. And so that is the place to look for dynamical evidence for a giant black hole. But what are the challenges? So first of all, there is a lot of dust. Well, lot is not the right word, but there are dust particles between stars. And when you're looking in the direction of the center of the Milky Way, although the number of particles, say, per cubic meter are extremely, extremely small, it's close to vacuum, there are a few particles per cubic meter, and because you are looking over such a huge distance, 26,000 light years, the distance of the center of the Milky Way from us, there land up being a lot of dust particles. And so that obscures the light from the stars around because dust particles tend to scatter the stars. So that is one challenge. And so the only way to peer into the heart of our galaxy is to look at infrared frequencies or radio frequencies. The other problem is because this is so far away, then the images are not so sharp. Whereas we need to look at stars really, really close to the center of the Milky Way in order to see any dynamical evidence for a giant black hole. So, and the reason why the images are not sharp is because we have our atmosphere between us and the cosmos, and the atmosphere undergoes density fluctuations which result in refractive index changes. So if you're looking at a star in the sky, instead of the light rays coming straight onto our detector, the light rays keep dancing around. And so we see not one image, but a whole bunch of images over a very short interval of time. So this dancing around happens at a very high speed. And so that is why normally we will not be able to see very sharp images, we see blurred images. Now, Andrea Ghez was an astrophysicist who joined the University of California, Los Angeles in the 90s, and she came up with the idea of using the newly constructed Keck telescope to look at the center of the Milky Way, because this telescope had a huge mirror, a mirror of diameter 10 meters, and therefore it could collect a lot of photons, and therefore with very, very short exposures, it could take images which could catch this sort of image of the star before it would dance and jump to a different position. So this was a technique that was known as speckle imaging, and using this technique, she and her collaborators imaged the heart of the Milky Way and started to see stars there using infrared frequencies. And so here is an example of the kind of data that they got. So what you see here, they look like clusters of some sort of not nice looking clusters of points, but actually each of these clusters represents a single star. And why you see it so messy is because the star has been dancing around. but they were able to catch it enough to distinguish that here is a star, it's dancing around a little bit, yes, but here's a star, this is a different star, this is a different star, etc. So they were able to actually separate out and image these stars very close by, and then by taking images at different time intervals, they were able to see how these stars move. And not only that, a few years later, their technique advanced even further. So this is just showing you that each of those cluster of points is a star, and by doing this offline calculation, they were able to discern that these were separate stars. And then they did something else, which is that they used the fact that this huge 10-meter diameter mirror is actually not a single mirror, but a segmented mirror with each segment as a hexagon like this and all pasted together. So therefore, each segment could have a control behind it which could manipulate how it is oriented. And what they did was to have the telescope fire a laser beam into the atmosphere and measure the refractive index distortions, feed those distortions back into their system, and use that to control each of these segments in order to compensate for the distortions that the atmosphere is making. And using this technique, and you can see here an image of the planet Uranus. On the left is an image without using the technique, which looks very blurry, and on the right is using the image, which looks very sharp. And so using this technique, her team was able to much improve their imaging. So the imaging started in 1995 and is still ongoing. Similarly, Reinhard Genzel was an astrophysicist in Germany who used their telescopes in Chile to do pretty much the same thing. And what did they find? So I'm going to show you what they found, but you need to understand what I'm trying to show here. So I'm going to explain that first. So this is an example of the image of the center of the Milky Way that they took, and the multicolored splotches that you see, each of them represents a star in the center of the Milky Way. It's a false color picture taken in the infrared of stars. The star shape that you see is not nothing, it's not any data, it's just there to mark a certain position in the sky, and you will soon see why that position has been marked. And on the upper right corner is the date. So what you will see is an animation which shows you these images taken at different time intervals and then all put together to make the animation. And so what does the animation show? Can you see the animation?
Yes.
Okay, so you can see the date on top. So now it's gone to 2003 and so on, and it will go up to 2020. And you can see these curves which are drawn, which are not real data, but you can clearly see the stars are moving, and the curves are the paths that these stars are taking, and they've been drawn to guide your eye. And you can clearly see that these stars are not moving randomly. They are not moving in straight lines. They are making elliptical orbits around a point, and all of them are making elliptical orbits around that same point. That is why that point has been marked with a star. So now this is very reminiscent of our own solar system, where you have the sun driving all the planets in elliptical orbits around it due to its gravity. And that is what we call Keplerian orbits. You will remember from your high school that there is a relationship between the mass of the thing that is driving these orbits, the speed at which these things are moving in their orbits, and how far they are from that central mass, right? And so if you know the speed and the distance, you can calculate the mass, and the mass comes out to be extremely large, in fact 4 million times the mass of our sun. Not only that, this star, which is very, very close to that point, you can see that it makes an ellipse and then emerges around without any deviation from its path, which means that whatever this massive thing is has to be smaller than the closest approach of the star, because otherwise it would have collided with this this massive thing, and then its orbit, you would have seen it deviate, right? So we don't see that. So this mass of 4 million solar masses have to be smaller, than much smaller than this closest approach, and therefore these scientists concluded that it had to be a black hole of 4 billion times the mass of our sun. So this was the first direct evidence for a giant black hole in the center of a galaxy. After that, there have been others. So you will remember that in 2015, two black holes, the coalescence or merging of two black holes were discovered using gravitational waves. And I will not go into much detail about it. I recommend that you listen to the announcement of this discovery, where Gabriela Gonzalez, who is one of the scientists as part of the collaboration, gives a very, very evocative description of their results. And in 2017, the team won the Nobel Prize in Physics for this discovery. So this was the second direct evidence for the existence of black holes. And the third was the discovery of the black hole silhouette in 2019. Again, I won't go in, this is a story for another day, because it was a very complex methodology that was used to discover this black hole silhouette. So we have these three pieces of direct evidence for giant black holes in the center of galaxies, or for any black holes at all. So as you know, oh sorry, I made a mistake here. The black hole at the center of the Milky Way won the Nobel Prize of Physics in 2017. I made a mistake here, it's not 27, sorry, in 2020 and not in 2017 as I've written here. Now, what was unusual about this Nobel Prize was that the media made a big deal out of the fact that one of the recipients of the Nobel Prize Physics in 2020 was a woman, and she was only the fourth woman to win the Nobel Prize. The first one was Maria Skłodowska-Curie in 1903. The next one waited another 60 years, Maria Griffith-Meyer. And then the third one was in 2018 to Donna Strickland, and then 2020, Andrea Ghez. So when typically I ask people, why do you think this is? And I give them some options. Is it that girls are not interested in science, or is it that women are mostly too busy taking care of their families and therefore they cannot spend time doing physics? People tend to choose the latter option as probably the reason why there have been only 4 people who have won the Nobel Prize in Physics and who are women. However, there is this whole list of women who did transformational science in physics even. So here I've listed a few of them. This is Cecilia Payne-Gaposchkin, this is Bibha Chowdhury from India, Vera Rubin, and Jocelyn Bell. All of them did transformational physics but did not get the Nobel Prize. So Cecilia Payne-Gaposchkin actually discovered that stars are made mostly of hydrogen. At that time, it was thought that stars were made like the Earth, like, you know, we have rocks and stones on Earth, and it was, they had thought that similar composition was what stars were. And she discovered, using Meghnad Shaha's theory and her own observations, she discovered that no, stars are composed mostly of hydrogen. And one of the famous astrophysicists at the, a few years later, at the time, she was that was not recognized. In fact, she was discouraged actually, and she had to sort of weaken the strength of that result in her own thesis. But a few years later, one of the famous astrophysicists described it as the best thesis in astronomy until then. I won't go into individual stories. All of you know, like probably know, that Vera Rubin's science got the Nobel Prize, but after she had passed away, Jocelyn Bell's science won the Nobel Prize, but she did not get it. Only a PhD supervisor got it. Now, Andrea Ghez has said, now so this is a very interesting article that came in the Scientific American, written by the Keck Observatory director, who also was at the Keck Observatory on the technical team when Andrea Ghez started her work trying to image the stars in the center of the Milky Way. I would urge you to look at that. And so she dedicated her PhD thesis to all the women scientists she knew. And she said, I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you'll get into MIT or Caltech, and so on. So, given this background, I wanted to talk a little bit about why is there a gender gap in science in India? What does the evidence in India show? So this is typically the list of reasons that people give for it. So I want to examine what does the evidence tell us vis-a-vis these reasons. So is it a lack of interest in science among girls? So before going into that, I just wanted to quickly remind ourselves, especially those of us who are science students, because we don't learn this in our college curriculum or anything, that sex is biological, whereas gender is socially constructed. We learn about it through our education and culturing and all of that. And a social construct is something that does not exist in nature, but is invented by society, and we all act as if it exists, and by our tacit agreement, it does exist. So examples of some gender-related social constructs are, for example, that men should not wear saris or skirts, or women don't drive buses, or women don't play the nadaswaram. So here, for example, is a photograph. This is a person called Mamata from Bengaluru, and she had come for an astrophysics outreach talk that I gave, and Mamata is a bus driver. And here is a picture of Karachari Mehboob, who won the Padma Shri for playing the nadaswaram. Okay, so let's look at why is there a gender gap. Is it a lack of interest in science among girls? Now, there was a survey which has been published in Current Science by Malhotra and Joshi of 4 schools in Dehradun, high schools, where perceptions of students were tested. So first of all, in this survey, a minimum of 30% girls said they like science subjects. If you look at the Inspire student fellowships, more than 50% are won by girls. The Indian Academy of Sciences summer fellowships, more than 60% are won by girls. And the Inspire fellowships, you all probably know that it takes a lot of doing, it takes a lot of studying and preparing for these exams to get the fellowship. And so it can't be that girls are not interested if more girls than boys are winning the fellowship. So it can't be that. So is it systematically lower competence among women? Today, nobody would dare to say that, although some people might still believe it. But there are also data. For example, a survey by Kumar in 2001, which showed that there is no productivity deficit among women with respect to men if you look at scholarly publications. And a survey done by Subramaniam in 2014 said that there is no competence deficit either. There are more women rank holders employed in research, and there are fewer women with lower university ranks compared to men in research. So it can't be that. Is it socialization leading to girls feeling incompetent in science? I had not realized this for a very long time, because I went to a girls' school in college, and in my school, it was only my Kannada language teacher and my music teacher and dance teacher who were men. Everybody else were women. Similarly, in college, my physics, chemistry, maths, and biology faculty were at least 50-50 men and women. So I never grew up with this idea that I could not be a scientist. But that did not persist when I went to the more elite institutions, where there was a huge genderization of studying, namely in IIT and later in TIFR. So it is important to look at is socialization leading girls to feel incompetent in science, but I don't know of good data about this. However, if I go back to the survey by Malhotra and Joshi, what they found, they tested perceptions of students, and they found that this idea that fewer girls than boys are interested in higher studies in science and maths are held more by the boys than the girls. So more boys than girls said yes, more girls than boys said no, and more boys than girls said don't know. Similarly, there were these other perceptions. Girls are not good at science and maths. Girls find science and maths difficult and go for the easier subjects. All these perceptions were held more by boys than by girls. So it seems to be that although I don't know the answer to are girls socialized to feel incompetent in science, or rather we don't know, we don't have evidence to support that or not support it, but certainly there is evidence that boys are socialized to think that girls are bad at science, and then these boys will grow up to become scientists and then take decisions in scientific institutions and so on. Okay, so what about discriminatory familial responsibilities on women? This societal expectation that is discriminatory on women, making them responsible for caregiving more than men or unequal to men. So there was a global survey of physicists in 2014 which reported that for India, 62% of the scientists who responded to the survey reported as being in a long-term relationship or being a parent or guardian. But 77% of the women, as opposed to only 53% of the men, reported that careers change their personal decisions. So it could be that this is a factor, the discriminatory expectations from society that women should shoulder the caregiving responsibilities more than men can have an effect. However, it can't be the whole story because the gender gap in physics is higher than in other subjects. So this is statistics for PhDs in science employed in higher education in India. And for all sciences, the female fraction is about 45%. This was way back in 2015. And for physics, it is 19%. So it can't be the whole story. Discriminatory familial responsibilities can't be the whole story. So then I'm putting a dotted ellipse around it, and I want to look at discrimination within the profession. So within the profession, again, the same study by Neelam Kumar found that women are systematically lower in the science hierarchy compared to men, despite there being no productivity deficit among women. And the mean age of women who were professors or equivalent was significantly higher than that of men. And she concluded that there is discrimination within the profession. This is what we also found in our own study. So I already said that the physics PhDs employed in higher education in India are only about 20% women, which is already skewed. But if you take that at face value, and then you look at what is the fraction of women in the Indian Science Academy, for example, among physicists, or the prestigious Raman Memorial Lectures, or institution governing councils, physics institution governing council, this drops hugely to single-digit numbers, right, from that 20%. So clearly there is discrimination within the profession. So one thing to remember is that the government of India has always recognized this. As early as 2008, the Minister of Science and Technology made this statement. It seems to me that we have developed in science and technology a stratified system in which men are favored with career advancements at the expense of women. But acknowledgement within the physics community has been extremely slow in coming, and this is the reason why, even though we are now in 2021, there hasn't been that much of progress. So I just wanted to give some experience of what we, some of us did through our professional society, which is the Indian Physics Association. And so on Women's Day 2016, I wrote a proposal along with a bunch of other senior physicists to form a working group on gender equity in physics under the Indian Physics Association. It was formalized in 2017. It built on a working group we already had in the Astronomical Society of India. Following this, we brought out two special editions of science publications, namely Resonance, which all of you may be familiar with, and also Physics News, which is a bulletin of the Indian Physics Association. And these special editions had an all-women authorship. The only idea was to show that women are as competent as anybody else to write for a range of audiences about the science that they do. Right? And then we had a kickoff event, which was called Pressing for Progress 2018 in Bengaluru, hosted by ICTS TIFR, which is on YouTube, so all of you can look at it. And that was the first time that sexual harassment within the physics profession was openly discussed in a formal forum. Now, after the formation of the working group, there has been some change. So, for example, the C.V. Raman lectures, which had this kind of a distribution before until 2015, has now increased over 30%. Similarly, there is something called the R.D. Birla Memorial Award, which is recognition of research in physics by the Indian Physics Association, and until 2017 there were no women laureates at all, and now there are at least two. So at least this is changing from a full red circle to this. And I want to emphasize that it's not just about having women in these committees or having this working group. It is also about raising the discourse and raising discussions and constantly talking about how there are barriers within the profession to achieving gender equity. So another major accomplishment of our working group was the national interdisciplinary first of its kind conference we had in 2019 called Pressing for Progress. And I won't go into the details, but from the conference came out something we call the Hyderabad Charter for Gender Equity in Physics, and we are seeking endorsements of this charter from physics PhDs in India, and it is very heartening that several leaders and past leaders have endorsed the charter, and the national leadership has also taken note of our recommendations. But what is this charter about? So the charter is about making physics welcoming and healthy for all genders in the spirit that science is a global public good. So the fundamental principles of the charter are articulated this way, and nobody would really argue with that. But the important thing is to recognize that we are a flawed meritocracy and we need to fix it. In particular, we need to stop fixing the women, and we need to focus on making our enterprise welcoming for all genders. So these are the guiding principles of the charter. And for example, it says gender disparity in physics is due to both patriarchy in wider society and gender bias within the enterprise. So this is important. So we cannot always push it on outside society, because we, after all, are also society, and we are going to be reflecting whatever is happening in outside society. We are saying that we need interventions because time alone won't fix the problem. We are saying that the quantitative gender gap at all levels is a symptom of the gender gap and it needs to be fixed, but it is only necessary and not sufficient to achieve gender equity. And therefore, we need to transform the culture of physics in order to make all talent feel welcome and acknowledged and used. And we need to recognize that the practice of physics is a social activity. And so addressing gender bias does need insights from the social sciences. This is very important. So what does it mean to endorse this charter? It means that we broadly believe in the text of the charter and that we as individuals will work in our own spheres of influence in order to use the charter to raise discussions, to raise dialogue, and come up with interventions. So, for example, our own spheres of influence could be that we are a teacher in the classroom, we are a faculty hiring member, we are running a conference, or we are on some editorial board member, and so on. So, some easy things are that all institutions should have a gender audit and should publish that on their organizational webpage. Institutions should adopt gender neutral language in their forms, in their documents, and in daily practice. In classrooms, all students need to be held to the same standards regardless of their gender, and we should, in particular, not give mentoring advice and career advice differently, whether the students, depending on the gender of the student, because typically what happens is that we land up reinforcing stereotypes when we give career advice and when we mentor students. Conferences, for example, this would be one step. I'm not saying this is the final thing, but this would possibly be one step towards making a conference feel welcoming of all genders, where you say, instead of saying just having a registration box saying gender and then just 2 boxes or even 3 boxes saying female, male, and other, you have a larger number of boxes which includes things like prefer to self-describe for gender. We have recommendations on work-life balance policies such as childcare leave and mobility schemes should be gender neutral. So any work-life balance policy should be gender neutral and should be available to both men and women. When workshops are done, now it's very common to have workshops in the name of enhancing gender equity. It's very common to have workshops exclusively for women to enhance their research skills, to sensitize them to legal, even emotional intelligence workshops. And this is just not okay, because this is just subscribing to the notion of fixing the women, whereas what we need to fix is the climate in our profession. So, for example, criteria for hiring should be formulated beforehand. There should be no hidden norms. There should be no age bar. The hiring process should provide full information, full transparency to all their candidates as to what is the process, what is the timeline. The status, position, and background of a life partner should not be a criterion in hiring, and so on. Most important, I would say, gender sensitization training should be mandatory and not only for students. It should be mandatory for the whole level, right from senior management, directors, deans, etc., right through all the faculty, regardless of their gender. Because the point is that we are all, regardless of our gender, raised and brought up to accept sexist thought and sexist action, and therefore we are all vulnerable to gender bias, and therefore we all need this gender sensitization training. So I will stop there with this cartoon that was published in the Resonance magazine that I mentioned earlier, published in March 2017, where we got a woman cartoonist to do this cartoon for us. Thank you very much.
Thank you so much, ma'am, for sharing your vast experience from research to your experience with the issue of inclusion. So far we have seen an insight from an astrophysicist on and her take on inclusion. So I think now we will get a chance to look into a chemist's take on inclusion. So we will. So without much ado, I'll hand over to Bhavika to introduce Professor Khushalani. Over to you, Bhavika.
So now let me introduce to you our next speaker and distinguished guest of the day, Professor Deepa Khushalani. Professor Khushalani is currently Professor in the Materials Chemistry in the Department of Chemistry, TIFR, Mumbai. Her area of expertise involves synthesis, characterization, and application of a variety of inorganic structures such that the morphology, phase, and size are carefully manipulated so that there is precise control over homogeneity and compositional purity. The ensuing materials are applied in the areas exploiting alternate sources of clean energy involving photovoltaics and energy storage devices. Professor Khushalani has been widely recognized for her work, some of her laurels including CRSI Bronze Medal in Chemistry 2018, the DST Young Career Award in Nanoscience and Technology 2016. She is a Fellow of the Royal Society of Chemistry, holds a chair of RSC West India section, is an editorial board member of Scientific Reports, Nature Publishing Group. Moreover, Professor Khushalani, with specific relevance to today's gathering, is a member of Indian Academy of Sciences, Women in Science Panel, and Royal Society of Chemistry UK Inclusion and Diversity Committee. She is extensively involved in science outreach, actively promoting basic sciences within rural and economically deprived areas of India. To this end, she has given lectures and conducted workshops and mentoring sessions. With this small introduction, I would like to hand over to Professor Deepa Khushalani to take us ahead in this session.
Thank you, Ms. Bhatia, and thank you to Ms. Biswas as well and Dr. Agarwal for the invitation. It's a pleasure to be here. And I was at a loss, I will be honest, when I was requested to present some of my experiences at this meeting, at this seminar that you've initiated on inclusion and diversity. I was a bit lost simply as to how to present some of the ideas that I have. And considering it's the chemistry department of St. Xavier's that has invited me, and considering the fact that all the audience members are, I assume, are involved in some form of scientific study or endeavors or research or teaching. So I thought, how do I sort of amalgamate all of these things into something that is interesting for the audience? And I have to give credit to the previous speaker. She was able to talk extensively about her science fantastically, and also about her efforts into improving gender diversity and inclusion of more females into the Indian science streams. So to begin, so the title of my talk was, is it a moral obligation to pursue your dreams? Because I put this title, and I hope you can see my screen, simply because it's something that I have realized is an interesting way of looking at how to pursue your ideas in life, which is because it comes always with lots of questions. And sometimes you are at crossroads and you do not know what to do, what to pursue, how to pursue certain things. And you know, sometimes society puts pressures, as is very obvious, and this goes for every type of human being on this planet, because there is no stereotype, be it a male or female, person who is disabled, who's not disabled, who has issues with being some part of a minority, be it a LGBTQ community, be it in terms of having some sort of an impairment or disability or what have you. So physical disability, mental disability, and the idea is that at the end of the day, we are all human beings on this planet. We're here to live a productive life. And what does it mean to be productive? And usually it means that you have some idea of what you want to do in life and you would like to pursue that. And I want to sort of bring in this question of basically, are you obligated to pursue your dreams, or is it important to compromise on your dreams as you go through life? So I don't know if I have the answers to all that, but I want to sort of present that. But before I get into all of those aspects and how, you know, how do you go about doing something tangible? What I'd like to also give you is some ideas, especially to the students, which is something that you can take away with you, that you can apply to your real life. And I'm going to use examples from my own life, because I am not a philosopher, I am not a psychologist, I'm a chemist. And but just from my experiences, I want to sort of give you some ideas as to, you know, how I dealt with certain situations and what aspects are important in life as you go through, you know, your career, as it were, and your studies. But before I do that, I thought I would present a little bit of science. So bear with me as I divide up my talk, and I'm going to talk about the science relatively quickly, but I think it's important for the audience to appreciate that all of us are scientists and that we do pursue, what we pursue is a passion. And I want to share with you my passion. So I'm a chemist, I'm a materials chemist. And what we work with are inorganic structures. And what we do is we play with their architecture. We manipulate their shape, their morphology. And here you see in one slide how you can change the shape of a very simple material, chemical called silica. It's very similar to sand that you see on your beach. But here you can see the shapes have been changed, and the shapes are on a nanometer to a micron length scale. And what you see here basically is something that when you change the shape, you can change their applications. And the idea is that you can work with hollow capsules here. Maybe I'll just turn my thing into a laser pointer so you can see that. So these are hollow capsules. They're used for drug delivery. And in this case, you see this very interesting architecture, which is sort of like a honeycomb, but where you have very ordered porosity. And this is called a photonic crystal. It's an incredible device that allows you to manipulate light. You can bend light using the refractive index. In the middle here, you see mesoporous silica, which can be used as a catalyst. What I want to talk about the passion that we use these materials for is something to do with an issue that's very paramount for India. So I just want to give you a little bit of background. We all need energy. We need energy for all of these issues. But the problem is in India, when we use energy, it comes at a huge cost. It's not only about a financial cost, but it comes at another cost. And what I want to highlight is that it affects India more than any other nation on the planet. Is something that you need to consider, and simply because of the population. This is the current population according to the world data. And as everybody's familiar, we are around 1.3 billion people in this country, and we are second in the world. However, this is not going to remain like this over a period of time, and this is over the next 45 years or so. What we are going to have is that India is going to surpass China dramatically, and we will be the most populous country in the world. So why do we worry about the population? Why am I bringing this into my talk? Remember, I just gave you a brief idea about energy. Well, I want to talk about the quality of life that we have currently. There's something called the Human Development Index. You can look this up. And India is located here. As you can see, it's not located very high on the y-axis. What I'm not showing you is the x-axis currently. The y-axis is this score, is this index score that the United Nations has come up with. It's called the Human Development Index. And this index, the higher the number, the better is the quality of life you have in your country. And it's about, the average age, the medical services, the quality of education, transportation, pollution, and various aspects. So gross national product and so forth. And as you can see, India is not very high. What I'm not showing you is what is on the x-axis. It's not, what is Human Development Index associated with? Well, it turns out it's associated with electricity consumption per capita. So which is that the more electricity you consume per person, you will actually move up on this axis, all right? And that is important. Remember, I showed you that India is going to be the most populous country. Therefore, in terms of the electricity requirement of our country is going to be substantially large. We're going to have a huge burden in terms of where this electricity is coming from. And this is paramount for us to improve the quality of life that we have as a society. All right. The two things go hand in hand. So why do they go hand in hand? Because, and where is this electricity coming from? It's coming from, consumption of oil and non-renewable resources. And there's a link. Therefore, as time has gone on, and this is just data, I hope I've just highlighted the important things in red. I want you to see that just for India, from 1990 to 2016, the human development increased 1.5 times. Okay, the energy used did also increase 1.8 times. So there's a direct correlation. But when we use more energy, we release more CO2. And CO2 increase per person also increased during this period. And what happens when you increase CO2? You increase pollution. And why are we increasing CO2 when we talk about energy supply? Because in India, most of our energy supply is coming from these non-renewable resources like coal. Okay, so the population is increasing with time. This higher population needs more energy. When this higher population needs more energy, it's burning more coal. When it's burning more coal or oil or other non-renewable resources, it's releasing more carbon dioxide. When it's releasing more carbon dioxide, you're leading to pollution. All right. And I don't know what's happened to my so this is the kind of pollution we're talking about. And just to give you a, something, this interesting image I want to show you, which is, it's from the right side. This is India Gate, obviously in New Delhi. And this tells you about how we deal with where pollution really comes from, at least air pollution. This is from The Guardian, and the right side image, okay, is from around April, May 2020, which was last year, which was at the height of the COVID lockdown. At the height of the COVID lockdown that was there nationwide and in Delhi, we did not have trucks and cars plying our highways and roads. And because of that, we were not burning as much non-renewable sources of energy, sort of with diesel and gasoline and so forth. And therefore, air pollution came down substantially. And look at the stark contrast with what is there on the left side. And on left side, you have basically the conventional pollution that now exists because now the cars are riding again. So, as you can see, it's a huge problem in India, and we cannot get away with this problem easily. So this is where I, as a scientist, I, as a chemist, we try and contribute to try and improve things and see if we can circumvent our dependence on these non-renewable sources of energy. So we work extensively in our lab with respect to energy capture, which when we talk about energy capture, what am I saying? I want to basically take sunlight and I want to capture it and I want to convert it into a form of energy that we actually need, which is electricity. Hence, we want to work on solar cells, and we work on devices as solar cells. When I talk about storage, what am I talking about? Energy storage. A solar cell does not store energy. So for storage, I'm talking about batteries. The batteries that go into your laptops, into your mobile phones, into the electric grid. We want to be able to store sun's energy during the day so that we need it at night, and how to do that effectively. And we also want to talk about conversion of that energy. And it does not mean that we want to convert sun's energy only into electricity. We can also convert it into a chemical energy. Can we use sun's energy and drive chemical reactions and make viable chemicals that currently need lots of other types of catalysts that are not always very effective? So I just will give you a little bit of science, and then I will proceed to the second half of my talk. So this is what I mean about solar cells. So I'll just tell you how a chemist can contribute to a solar cell device. So what you see here on the top left side is what these third generation solar cells look like. Okay, as you can see, they're multi-layered materials. It's like a sandwich with lots of layers, and the two slices of bread in the sandwich are nothing but two electrodes. Okay, and which are the two electrodes? So this cross section sort of shows you the electron pathway. And I just want to highlight what is the most important thing is this red layer. It's given the word perovskite. Don't worry about these names. Suffice it to say, what are we working on? We're working on a concept. The solar cell works on a very simple concept of taking photons of sun's energy, and the sun's spectrum is there. There are lots of visible light, and there's lots of UV light and sort of infrared radiation is available to us. We want the photons, and we want these photons to be absorbed by a material, ideally one material. One material does not always absorb all the photons because it needs to be black. But the fact of the matter is, whatever material you have, you want to be able to absorb it. So here in this little cartoon, you see this quickly yellow line coming in, which is sun's energy coming in. What happens? The material inevitably needs to be a semiconductor, and it goes from a ground state to an excited state. Okay, And what we want is we want to capture the excited state. The electron goes from a ground state to the excited state. It has captured this energy. We cannot capture all the energy, and we want to remove it out of the material. So all these layers are these layers that help you extract the excited state. Okay. And this is how you characterize it. This is sort of an IV curve, and this orange curve is better than the blue curve. So these are sort of kind of signatures of how you make better solar cells, because what you do is you play with these layers. All right, there are 3 layers in terms of the 3 electrochemical potentials I've shown you. The HOMO-LUMO, you understand, this could be a molecule, this could be a valence band here, and this is a conduction band. This band gap is important, and what you want to do is create this excited state, and you want to prevent recombination, and you want to be able to extract the excited electron, and this hole goes in this direction. So the hole goes in one direction, the electron goes in this different direction, and that is where you separate carriers. This excited electron that comes out of this electrode is that then does work for us. Okay. And so this is basically a quick guide of what a solar cell does, and we play with these layers. Why? What do we mean by we play with these layers? We play with the chemical composition of these layers. We want good band gap materials. We want them to be stable. We want them to generate lots of electrons, and we want these electrons to be extractable easily. We also play with the other layers so that the potentials of these other layers are important. You don't want to lose too much energy, so the potentials of these materials are important. The interfaces are important. So we work with high surface area structures, so you have good intimate interaction between all these layers. Okay. So this is what goes into research about how a chemist can contribute, and I'm showing you various structures there. And these are our devices. We also work, remember what I said about energy storage, but we're working on a very interesting concept about energy storage, which is we're working with materials that can not only capture sunlight, but hold on to it. You see, in a solar cell, I have to remove that excited electron. If I don't, it will recombine. When it recombines, I lose that energy. However, we want to basically store that excited electron in a battery. So the idea is that we're making what is called a solar battery. Right now, what you see here on the left image is what is conventionally done. You have a solar cell, and the solar cell is coupled to a battery here, right? The solar cell generates the electrons, and these electrons get stored in a battery. What instead we want to do is, can we just use the battery directly with a transparent electrode, that when I shine light on the battery directly, it will charge itself. Think of it from a conceptual idea, which is when your mobile phone currently loses its charge, you have to plug it in. What we want to do is we want to have the back of the mobile phone to be transparent with a transparent electrode and an electroactive material, and you just put your phone in sunlight directly and it will charge itself. And the idea would be, wouldn't that be nice? It's about the chemicals making up the battery material. It has to be redox. There's a lot of redox behavior in a battery. Reduction, oxidation happen in a cyclical way. And we're trying to play with semiconductors that have that behavior. Okay. We have lots of other projects that we work with. It's not only energy storage, but like I said, we also work on energy conversion. We talk about splitting water to make hydrogen molecule, hydrogen gas, which is fuel of the future. Which is here shown in the bottom left. This is and we also work on drug delivery devices. These are hydroxyapatite nanotubes that are very effective for delivering cancer drugs and so forth. Okay. So at this juncture, I'm not sure how to deal with time, but at this juncture, what I'll do is I'm going to sort of stop talking about my science and give you a little bit of an idea as to, my history and what made me pursue science. And the idea is that I hope just by talking about some of the experiences that I've had will help you understand, that the path to success. I'm not saying I'm successful. What I'm saying is the path to anyone sort of wanting to decide what to do in their life involves a great deal of personal ambition. Okay, and I want to talk about certain skills that I think are important that all students regardless of where you come from, regardless of your status, minority status, in whatever way you have that, how you can try and ensure that you have a meaningful, productive, successful life on your own terms. Okay. So I'll just tell you something, a little bit of the fact that where I started. I was born in Delhi, but we did not live in Delhi very long. When I was about 9 years old, my parents emigrated to a place called Trinidad. It's in the Caribbean. So I did all my early schooling before the age of 9 in Delhi. But after the age of 9, from the age of 9 to 16, I was in this island called Trinidad where I did my high schooling. So that was a huge change. And it was good and bad because there were no other Indians there. The food was very different and life was not easy. But, you know, I was the only Indian student and surrounded by lots of Africans there, the Caribbean natives, as it were. And it was a very interesting experience. So at the age of 16, then my parents moved to Vancouver in Canada. And I did one last year of high school in Canada, and then I did my Bachelor of Science there in chemistry. And at that point, I lived with my parents, and my parents were very happy that I was pursuing BSc, because what they thought that is that I should, with a science degree, I should become a teacher or a doctor. And I didn't want to do either of those two things. And at that stage, I decided to move, and this was me moving only. My parents stayed back in Vancouver, and I moved to Toronto, which is on the East Coast, and I did my PhD. This was not due, I did not have my parents, they were not very happy with that decision, but they let it happen. And I'll tell you why I did a PhD. The sole reason I did a PhD was because of financial independence. You see, when you do a PhD in science, they pay you. You do not pay. You have very small tuition fee, but you get a monthly stipend. And that allows you not to, at least it allowed me not to be a burden on my family. Because I wanted to study after my BSc and I didn't know what to do, but I realized that if I pursued a PhD, that I would not be a burden on them. See, my parents, my father is an engineer, my mother is a housewife. So it was, you know, life was not easy in terms of finances, and it has never been easy, but anyway. So I did my PhD in Toronto. After that, I moved to England. And in England, I did my postdoc for a few years, still trying to find what it is I wanted to do. And I got accepted into a faculty position in a university. I was teaching for a few years there. I was a junior most position, assistant professor, sort of a lecturer there. But after a few years, I decided to return back to India. And at the age of 34, I came back to India and I got a job at TIFR. And I've been here ever since, which is now about 15, 16 years ago. Okay. So I've had a very circuitous route in terms of my education, but I started and ended up in pretty much the same place. And so the idea is that, you know, having all this experience, I hope will allow me to give you some advice as to what I think are issues that are prevalent throughout the world. And it's something that you have to decide whether you want to, you know, if this is the road that you want to pursue. And these are the things that I realized were important, and these skills over the life. So now I'm going to talk about the skills that most people are familiar with. And what I'm showing you on the screen are something called hard skills. They're learned through education or training. We are not born with these skills. And all of you, at least all the students in the audience, I hope, you know, I assume you're realizing this now, that this is what you're learning. You're learning hard skills. So you're gaining academic knowledge, you're taking chemistry courses, physics courses, biology courses, what have you. You're learning how to use, hopefully, some instruments. You're learning other skills like, you know, perhaps programming, typing is an important skill, proficiency in various software, speaking a foreign language, and so forth. And all of these skills are important, agreed. They're absolutely important if you want to be successful in life. But I would also like to talk a little bit about soft skills now, which is Here's a bunch of words that you might be familiar, you will be familiar with them. But you know, we don't get taught these things in any lectures, or there are no courses given on this. And you do not put these things down in your transcript. But these skills are equally important in life. And things like work ethic, interpersonal skills, time management, leadership, all of these things, you can decide whether you're good or not. And I'll just sort of give you an example of time management. You know, are you the kind of person who, when you get a homework assignment, do you do your homework assignment immediately? Or do you wait till, you know, your teacher gives you an extension upon an extension, and then you do your homework and submit it? This sort of skill or this behavior does not change with time, okay? And what you'll find is that this skill or this behavior will also affect you later in life, in your professional life, because there will always be time constraints, deadlines by which you have to submit a report, by which you have to give a presentation to your boss, by which you have to show some output, some sales goals, what have you. And if you think you're the kind of person who will always be tardy with your assignments, then this carries you later in life. And it's not actually a good thing. But if you're the kind of person who sort of does things on a timely manner, actually it's a very important skill and quality to have, because you will be far more efficient at doing things. And it will help you in a productive way, in an advantageous way later in life. Okay. By the same token, there are all these other skills, but you know, I'm putting down all of this. Now, I'm going to put a question down for everybody, which is, out of all the, you see, there's one thing like the hard skills, which is you can have an A+ in your chemistry exam and your transcript, and you can have fantastic data the mining skills, and you can have programming skills and so forth. But it's also these other soft skills that you need in life. And out of all of these soft skills, there are certain soft skills that are more important than others. And I'm going to show you, according to LinkedIn, what is the most important soft skill that people have found when it comes to getting hired and being successful in life. And it's communication. It's only a small percentage, but it's something that I have also learned in life is a very important skill to have. And I think it's something that students in India do not give enough weightage to. The ability to write, speak, read effectively. And it's not about a language. You can do it in Hindi, you can do it in your native language, but it is a highly important skill to have, especially oral speaking skills. The ability to talk about your science in a convincing way that allows the audience, whoever the audience is, it could be one person or it could be a group of 100 people. But question is, how are you communicating your ideas to ensure that you capture the attention of your audience? Okay. I'll give you a case in point, because life is not only about when you go and give a seminar. It could be that you are doing work in your job and your supervisor or your boss suddenly shows up at your desk and says, "Arey, what have you done recently?" And in that minute, how you're able to talk about what your work is in a way that makes him or her impressed is very important. Okay. And it's how clearly you talk. And therefore, and it matters, you know, are you talking to your 10-year-old nephew or niece and explaining to them about a science project you're working on? And are you talking to your teacher or to your supervisor and talking about the project you're working on? How effectively are you able to use the right words so you can impress the 10-year-old nephew when needed, but you can also impress the supervisor when needed? And you're talking about the same project. How effectively you do that is a very good skill to have. And I think the students need to participate in making sure that they get better at it. We are not born with these skills. Many people are, maybe they're innately very good speakers, but you have to inculcate the idea that you do things in a very clear, professional way. Same thing with writing skills. You know, I'll tell you what I mean by a writing skill, soft skill. I am a female who works in TIFR as a scientist, and as such, I get lots of requests from students who want to come and do summer projects or master's projects or whatever part-time projects with me. And they have obviously read my work, they have gone onto the website and they have looked up my data and looked at my area of expertise. But when they send me an email, the first line of the email says, "Dear sir, I have gone," and the second line says, "Dear sir, I have gone through your website and I've read your papers and blah, blah, blah." Now, if you go on my website, you will see immediately my picture. I put a picture on my website. So you know I'm female, but the fact that you've not taken effort to write the correct salutation shows a lack of professionalism. Small things like this make a big difference. So when we talk about communication, make sure you participate in including the rest of the community. Do not isolate yourself and do not participate in perpetuating the same prejudice. Okay, the reason we are at the state we are in terms of not having equal diversity is because everybody, all parts of the population, men, women, disabled, non-disabled, what have you, they all participated in perpetuating a bias. You can be a female and be very biased against females. So be careful about that. Understand your own biases, sort of conscious or subconscious bias. And you have, because we are society, just like the previous speaker said, and we have to participate in removing those barriers and therefore communicate clearly. And it's a very important skill to have. Okay, I just sort of highlight something, out of the top 10, look at the bottom one. It doesn't matter how friendly you are. You can get ahead in life regardless of whether you're friendly or not. But if you've got these aspects which are in the top, especially the ability to clearly talk about your work in an effective way is very important. Okay. Now, these are the other things that I want to talk about briefly as to the things that I think are important when it comes to pursuing your dream. Remember, the title of my talk is about a moral obligation. I think it's very important for you to realize, just like, we talk about the fact that it's your moral obligation to not lie. It's a moral obligation not to steal. It's your moral obligation to live in a civic society where you don't, destroy your environment and so forth. By the same token, I think it's important for people to realize that it's a moral obligation for you to pursue your dream. You should not compromise on your ideas of what will make you happy and successful in life. Okay? And one of the most important aspects to start with is that you must have ambition. It should be your personal drive. You should be self-motivated to say that I want to do X, Y, Z, whatever that is. You should not be waiting for your parents or your teacher or your girlfriend or boyfriend or your best friend, what have you, to be telling you, oh, you should do this in life. You should apply for an MBA or you should do an engineering degree or whatever. You should have your own idea and you will, instinctively. And those ideas, those desires that, those are the directions you see your life going. That is, you should be ambitious and maintain that ambition. That is where I think a lot of people, under the guise of sacrifice and compromise, start losing their way in life. And I think this is where you need to actively participate in your own life. Do not be a bystander. And do not say, I will do that later on. You get very few opportunities. Very few doors open at the right time. And you have to be available and ambitious to walk through those doors. And that is where you should be self-motivated. But think about it. If you are the kind of person who needs someone to push you all the time, you will have issues because then you're letting them drive the direction of your life. You're giving away ownership. And that you need to think about carefully, because then you will have to deal with the consequences of that. So this is where you need to focus. That's the second point. There are lots of directions around you. You need to realize that you might have lots of dreams, like you want to be a tennis player, you want to win a Nobel Prize, you want to be excellent in Bharatanatyam, whatever, what have you. We all have lots of dreams and so forth. It doesn't mean that you have to be academically excellent in the decisions you pick. I did not get straight A's in chemistry when I was young. And by young, I mean, at the time of board exams. When I say board exams, I mean that when at the age of about 18, 17, 18, when you're thinking about what to do, chemistry was my weakest subject. But it's something that allowed me to be, challenged me. And that is why I pursued it. And it sort of remained in my focus beam, as it were. There were lots of other directions I could have gone in, but simply because it was a challenge, it did not come easy. Then I would like everyone to be prepared to be confident. There's a fine line between arrogance, but there's also this concept that you must be humble, or you should show humility at everything. And I am not convinced that you need to always be in second place or in the background. Do not be afraid of being confident about your capability, but it's a fine line. Do not cross it into arrogance. Fine. Then the other aspect I want to highlight is something called perseverance. In fact, this, next to ambition, I think this is the other trait that is highly important when you want to pursue your directions in life, because inevitably what you pick, inevitably the directions you take, you will fail. There will be always times that you fall down. You might fail a course, you might not get a grant approved, you may not get access to the right institute, or you might not get enough funding, or what have you. There's so many ways of failing. But the most important thing is you have to get up and try again. And when you fail, yes, everyone says you learn from failures. You should learn from failures. Yes, you learn from failures, but more importantly, you should forgive yourself. You should not bog yourself down. Be sad, be upset when you fail, but you cannot drown yourself in that sorrow and say that I am no good, that I am incapable of doing this, that this is beyond my ability. That you have to stop yourself from going down that track and say, okay, I failed a course, I didn't get here, whatever the issue is. But if you don't have belief in yourself, trust me, no one else is going to have belief. Don't wait for somebody else to come and cajole you and say, "Arey, get up again and do something else." You have to find that, when we talk about inner strength, and this is about hard work of success. This is what I meant when I was saying in my abstract, which is, what does it mean when people say you have to work hard, if you have to be successful in life? It's paved with hard work. What is hard work? This is hard work. Hard work is you falling and you're getting up again and trying again. You're trying it in a more intelligent way. You're trying it in a different way, but you're not giving up. And you're forgiving yourself. Mentally, you're opening more channels so that you can be more successful. All right? Please keep this in mind, because these are the tricks that people use to make sure that they reach their goal. No one reaches the goal in one try. You have to try over and over and over again. But and if you have a fantastic support system around you, great. But whether you have it or not, you have to do it for yourself. Okay. Then there are a couple of other issues that I've brought in, which, it's about selfish versus selfless behavior. The idea is, when are you doing something in a selfish way? When you do some things in a selfish way, there's nothing wrong with that. And this is what I meant about moral obligation, about pursuing your dream. Because when you pursue your dream, many people will think that you're selfish because you're only thinking about yourself. But other people's happiness is not dependent on you. Your happiness is dependent on you. Please keep that in mind. And this is where I would like you to think about actively that how you decide the path you want to take. And the last one is independence, interdependence, and dependence. And it's question in life, you cannot be independent all the time, but in life, you cannot be dependent all the time either. And you have to find a good balance. That is, question is, when do you decide to let, you sort of be dependent on others? And when do you take control of your life? Are you the kind who relinquishes control easily? Or are you, participating in your life and taking active measures to pursue your dreams? So these are sort of, some ideas that I had that I put down. And finally, in terms of PhD, one thing I think people don't appreciate or they underestimate about what it is to do a PhD in science or why to follow a STEM career, why there's something called a leaky pipeline and all those issues. I just want to highlight some of the positive aspects about doing a PhD. A PhD doesn't mean that you will be a scientist only, okay? A PhD in science allows you to develop a fantastic problem-solving skill, basically, okay? And I'll give you a case in point. Currently, and it opens more doors, by the way, than it closes. So currently, if there's a dearth of something called patent lawyers in India. What are patent lawyers? Patent lawyers are lawyers who look at new discoveries made in science. You made a new cancer drug, you made some new device. They look at that discovery and they decide whether it's novel or not. And if it's novel, they write a patent and they award you a patent. When you own the patent, then you can get very rich because you own the ownership, the copyright of that structure. And therefore you can make a company and so forth. Now, these patent lawyers are very important because what do they need to know? They need to know science very well. They need to know science language and science ethos, but at the same time, they need to know law. So it's a combination of those two streams need to come together at a very high level in this sort of career direction. And there's a huge dearth because, you know what, we have lots of lawyers in India, but they just do not understand science. So they're not able to become patent lawyers. And patent lawyers are very wealthy people. And what, as a result, law firms currently do is that if you have a PhD in science, they will hire you. They will pay for you to get a law degree, which takes only a year or 2 years. They will pay you to get a law degree. You understand? So it doesn't cost you anything. And at the end of it, you will continue working for the law firm, but as a bona fide patent lawyer. They do not take lawyers and give them free PhDs because that is not easy. All right. It's a lot easier to become a PhD first and then go into the law stream. By the same token, if you want to get an MBA in America, universities like Cornell, a current MBA at Cornell and other universities, it's 2 to 3 years long. But if you have a PhD in science, they give you the MBA within 1 year because you've evolved and developed many of the skills already that with a PhD in science, only with that qualification, your MBA degree becomes 1 year long. So they realize the potential, the capability, the qualities you have developed during your scientific degree that allows you to be more proficient in other careers. People work on Wall Street. I have friends who have PhDs in science who work on Wall Street and those places now because they understand trends, they understand statistics, they look at analysis of what the data is telling them, and they are able to predict where some sort of Wall Street aspect is going to go in future kind of thing. So they hire PhDs, qualified PhDs. And the other, like I said, for me, the reason I did a PhD, and this is just from my personal experience, my parents were not very sort of happy with that idea at that time. and was simply because of the financial independence. And the reason that I continue to work as a scientist every day, even now, is simply because of the main thing, which is that the first sentence. Every day I'm learning new things. It is a challenge. It is not a boring job. And I don't have a 9-to-5 job, as it were. I do not have a boss. I come when I go. I come when I want. I go when I want. And the freedom that a scientific career affords you, I think it's fantastic. It's like a Peter Pan attitude, which is you're constantly learning, constantly doing new things. And because you are passionate about what you're doing, no one tells me what to do. I decide the direction of my research. And that level of independence, I think, is highly attractive. Okay. Plus, you get to travel a lot. I never thought I would get to travel so much, but in terms of conferences and networking, every year, I mean, before the COVID lockdown, we were traveling, or I would travel, 4 or 5 times. And just like the previous speaker, just like all the scientists you will come across, you will find that you have the ability to travel the entire world, fully paid trips by the government or your institute by travel grants. And, I think it's a very exciting and incredible life that I lead. So I'm going to end here, and I want to thank you for your attention. And this is a small group that I currently have at TIFR funding, and I didn't really talk about my research too much in detail, but I hope I gave you some ideas or some buzzwords that perhaps you can apply in your personal life that will allow you to hopefully pursue a very productive, viable direction. And, so thank you for your attention, and I'll stop here.
Thank you so much, ma'am. Your words were very relevant, I feel, especially to students like us who are just starting on a career path, and it's been really, really inspiring, to be honest. And as in terms of inclusion, I think your talk has given us a tool to understanding self-development, so as to be able to counter the judgment of those around us. That seems a very important aspect. So right now, after this, we have a group of student researchers who will be presenting on a very interesting project they're carrying on right now. So I will hand over to Bhavika to introduce them.
Now, we have reached the third session of this webinar, a presentation by 6 budding student researchers working actively towards inclusion. Let me introduce them to you. Jitin is currently a master's student at the Wildlife Institute of India, Dehradun. He is former POBE Fellow of the Jawaharlal Nehru Centre for Advanced Scientific Research, Bangalore. His current research interests are habitat ecology, behavioral adaptations, environmental communication, education, and gender. Jaisal is currently doing MSc Chemistry at the Gandhigram Rural Institute, Tamil Nadu. He is interested in chemical science, education, and social services. Hanan is a postgraduate in statistics from the University of Calicut. Her major research interests is in data and analytics. Asma B is doing her MA Psychology at Central University of Punjab, Bhatinda. She's interested in cognitive science, human personality, environmental psychology, and social service. Anu is currently an MSc Chemistry student at Farooq College, Kozhikode, Kerala. She's interested in chemical science, research, education, art, and literature. Srinath is currently an MA Sociology student at the Central University of Punjab, Bhatinda. He is interested in gender studies, feminism, sociology of religion, demographics, human rights, education, and social service. He is also part of youth wing of the International Human Rights Commission. As you can realize, this is a truly multidisciplinary team. So let me hand over to them now to go ahead with the presentation.
Thank you, Bhavika. Am I audible?
Yeah.
Thanks. First of all, our heartfelt thanks to Dr. Ashma and Bonaviti for inviting us to this amazing program. And without much introduction and other details, I think I'll present our study and I'll introduce what we studied and what all things we can discuss further.
So then we can move on to the question and answer sessions where we can discuss about the matter which we are going to present. So we are presenting this study, as you can see the title, we are decoding the women's career pathway in chemistry with special reference to Kerala. And you might be thinking what we are decoding and what we are actually doing, like how we can actually decode one pathway as we explain in, for example, some chemical pathway or some biological pathway, like we can decode, no, what are the elements including in that pathway, how some conversions happening, what are the external factors affecting through on the pathway. So similarly, you can imagine as a girl grow up into a woman, and she follows a career pathway, and obviously it will have lot of implications by the external factors or internal factors, and that will essentially mold the career pathway, and that will ultimately decide where she is reaching and how the process is happening. So decoding a career pathway is very important, because then only we can actually identify what are the influencing factors, like what are the supporting factors and what are the demotivating factors to someone who is trying to achieve something in the career pathway. But like some pulling factors and some pushing factors will be there. But most of the studies looked at the gender distribution in the career pathway, or whatever other similar studies have found that there are some factors, like general factors, for example, societal pressure or familial influence, like these broader categories we know, but exactly what are the factors are affecting this pathway. So this was our idea in the initial stage of our study, and then we decided a survey based and a interview based approach to actually look at the career pathway and to say like decode the pathway. So our study is titled Women's Career Pathway in Chemical Sciences, a multi-stage investigation in Kerala. And our study is supported by and funded by Royal Society of Chemistry Inclusion and Diversity Grant. So first of all, why this study? So if you can see the three questions, these are some common questions, but when we are thinking about the answers of these questions, we'll get to know a lot of things. For example, how many female chemists can you name? Or if you name a few key people in chemistry or any of the other subjects, for example, physics or biology or whatever, what will be the percentage of women on that particular list? Then now if you come to the student, like we are all students, and when we think about ourselves, how many chemistry graduates or how many biology graduates are actually staying in the field and contributing something to the society, rather than dropping out from the career pathway and doing something else? So these kind of questions are always in our mind, but we often ignore them, or like we don't care that much of these kind of aspects of our career pathway. So and the next question comes, why Kerala? Like why we choose Kerala to study this particular aspect? So whenever we're hearing the name Kerala, we obviously have that feeling of the one of the highly empowered state in terms of different indices. For example, gender empowerment index or high literacy rate, all those index which you can see in the green in color, for example, low fertility rate or higher mean age for marriage for females. All these things makes the state a unique situation or a unique environment in the country. But at the same time, for example, the study Mitra and Singh 2006 says that even though women in Kerala are highly literate and educated, they are still discriminated against the job market, or basically they're placed in the job at the lower end of the hierarchy. So this is a study looked at the point of view of a job hierarchy and all those things, but it is almost clear that it's the same situation is happening in the career pathway or in the educational field or in the industrial field, whatever else. So and generally in the country itself, as we get to know about uh, from the previous two talks. For example, Professor Prajval ma'am gave a like very like elaborate Indian scenario that was very interesting, and so I am not going to that kind of background. Then again, that background gives an idea that that leaky pipeline or the deficiencies in our career system or our academic system is there, but exactly what are the problems and how we can tackle them. So this was the motivating factor behind our study. And then we designed a methodology to understand the problems and come up with a study which will throw some light upon the factors which are affecting the career pathway, and possibly to give some of the policy recommendations which will be useful in the future. So initially we made a database considering all the entities related to chemical science in Kerala. So this included all the educational institutions, laboratories, industries, all the manufacturing units, then the research units. And we tried to include all the institutions from different sectors, private, public, and cooperative sectors. Now, due to the time limitation and other source limitations, we randomly selected around 12 percentage of the units from this database. And the initial database had around 4,000 sampling units, and we selected around 500 units from them. And then we contacted all these unit heads and asked them whether they're willing to participate in our study. And upon subsequent willingness, we asked the contact of their women employees in their institutions. Now then we decided, or we defined what all or whom are we like actually asking the questions. So we defined the our respondents. So the respondent should be a woman, and she should be currently working in the chemical science field, and she should have a minimum qualification of Bachelor of Science degree in chemical science or allied field, or a Bachelor of Technology also. Now so by this time it was already locked down, so we couldn't actually go to them and actually do an interview or a focal direct interview. So we initially initiated the study using a survey mode, and that also we converted into a online mode. So we administered an online questionnaire to all of these respondents and collected the data. So now, before I'm going to the data and all the other process, I'll give a like basically the survey based approach. Very important thing is the questionnaire, right? So how did we design the questionnaire and what all question we asked, I'll discuss later along with the other results. But the overall pattern was that we made a questionnaire and we peer reviewed, and then we did a pre-test survey among a selected sample population. And then after consulting their comments on our questionnaire, like how did they feel, should we change some of the questions, or like should we add more questions, like that we standardized our survey, basically the questionnaire. Then we did the original survey. It was spanning from 10 August 2020 to 18 November. Then we retrieved the data, cleaned the data, and we proceeded for the further analysis. So now let me come to the questionnaire. So what all things we asked? So basically the questionnaire was prepared according to the educational, sociological, and psychological aspect of the subject. And it was consisting of 72 questions with different response type. For example, some question we asked them to fill in a paragraph format, some yes or no, some like Likert scale, all these different kind of response types we included in the questionnaire. And then we did a peer review of the questionnaire from people in different fields to see how effective the questionnaire is. Now, the 72 questions we framed are basically, we can classify it into three different categories. The first category is family influence. For example, work family conflict or personal interest, all these things comes under family influence. Now, academical influence include curriculum influence or the gender issues they are facing in their academic institutions. Now, the external influence, for example, society, like obviously it giving some pushing and pulling, no? So to know that what are exactly those social factors, we ask some questions like that. And the environmental influence also, we ask some of the questions. Now, we also ask some of the demographic details of the respondents to see how are these demographic parameters are actually influencing the response of the respondents to a particular question. For example, the same question we are asking to different people, but obviously their answers will be molded by different characters and their society, their environment, everything. So to standardize that, we also collected some of the demographic parameters, which including age, their from where they are coming, and their educational background of parents, their academic qualifications, whether they are married or not, then their designation, all these things we asked. Now, before I'm going into the preliminary results we got, I have to give a disclaimer that all the results we are about to discuss here are preliminary in nature. We are still, this is an ongoing study also. So, but they are giving a lot of insightful results ultimately. So we'll discuss each of these results, but I'll go through all the result like in a fast way, because we have 72 questions, no? So, and plus a array of demographic parameters also we used. So there are a lot of results. I'll go through only the significant results we got so far. So our respondents, so basically we got a response from 201 respondents. This is the preliminary data only. Still we are processing the responses. And now the response rate from the institutional level was 87.77% and around 67% from the respondents level. Now, this included a wide variety of institutions, including high school and higher secondary schools, and arts and science colleges, engineering colleges, research institute, other industries, all these things. Now, we have a different sets of candidates or respondents from different backgrounds. For example, we have rural respond candidates, and semi-rural and urban, then from different categories, from different religions, so which made our analysis much more diverse in terms of the responses they are giving. Now, some of the basic like graphs you can see there. So one is the sector-wise distribution of the respondents. For example, you can see most of the respondents were from state government, and then the following one was from aided or finance, aided section, and then from central government funded institutions, and then private or corporate, and then cooperative institutions. And category wise also, we can see most of the respondents are from general category, and then from OBC, then followed by SC and ST. Now, what did we find? So now you know what all things we asked, kind of idea you must have gotten, and then what kind of respondents we had. Now, what did we find? So first we looked at their qualification or the profession they are choosing, or the designations currently they have. So as we expected, we found most of the respondents are from educational sector only. They are either assistant professors, or they are like teachers in high school or higher secondary schools, and then the majority of the people are research scholars. So either they are affiliated to some of the PhD courses, or they are working as some researchers under some funded projects. Now there is a very few people who are working as a postdoctoral fellow, or a research assistant, or a guest lecturer, all these different groups. Now we asked like an interesting question, like who was your PhD guide, or your PhD guide was a man or a woman or any other gender. So that question, I'm showing that graph right away. So the 76% or around 73% of the PhD guides were male. So we got this graph, and then we were like, okay, fine, this is something which we expected only. But then currently we are doing some of the focal interviews also. So most of them are saying like there is an inherent issue in the PhD guide. Like PhD guides are deciding whom I should mentor, and obviously the candidates will also have a preference in their minds, like which to whom I should get affiliated to for doing a PhD. So there is a conflict, and there is a high like gender gap, and then a gender issue also in that system. So we'll come into that later. Now one other interesting thing is that like you might be wondering, what are the pressure cookers we found. So we asked the respondents whether they had to face pressure from their family to get married during different educational level. For example, school days, graduation days, or post graduation days, or PhD. So what we found that, for example, school days, the second graph, it's showing that from Muslim community, Hindu community, and Christian community also there is a pressure. Like you can see the different percentage, and we found that the most pressure is coming from the Muslim community during the school days. Then we checked the same thing at the graduation level. So then it increased only. The 14% increased to 28% during graduation, and obviously the other two also increased. The other community also. Now when it comes to post graduation, it again increasing. It's becoming 30%, and in during PhD it's less. It's comparatively less, but still it's 20%. So so what was the question? I had to face pressure from my family to get married during graduation, or like generally the face pressure from family. Now that is a factor coming from the family. Now another question, or we asked the question in a different way also. My family and relatives were more concerned about my marriage than my PhD. So that is also giving the same kind of same kind of result. Now we asked about the restriction from the family, like apart from the pressure to get married, what are the restrictions from their family, which are affecting their career. So the same or similar trend you can see also in during graduation, school time, or post graduation, or whatever. There's the different communities are facing the pressure from their family, or the restriction from their family, to stop their career there to do something else, or generally they're facing a, like restrictions to follow their dreams or follow their passion or whatever. Now we also checked that the checked these responses at two different things, like whether the respondents are studied in Kerala, I mean inside Kerala or outside Kerala. So that also makes difference whether the respondents like did their graduation and post graduation and everything inside Kerala or outside Kerala. How did it matter? Now one interesting thing we found, here you can see, for example, PhD, I have found that women having children are facing many difficulties in completing their research works on time. So the respondents did their PhD inside Kerala told that yes, they are facing many difficulties, 82% of them. But the people who done their PhD outside Kerala, like obviously they also told that they are facing difficulties, but it's in a reduced way, 70%. Now similar trends you can see how like where you study matters actually. Now now we discussed about the restriction from the family or the pressure to get married. Now what happens after the marriage? Like after the marriage, obviously you have a life partner, and then there is a work and family conflict, all these things. So we asked some questions on that aspect. Now what we found that 14% of the married women faced forces to make changes in their career after their marriage. So the life partner or his family like forced these particular respondents to change their career, basically to deviate from the pathway they were intended to pursue. Then even though life partners of 83% of the women support them pursue their career, like it's an obvious thing, no, when you ask somebody that whether your life partner supports you to make more advancement in the career or generally support in the career or whatever, they'll say yes, yes, they are supporting. But to the same people, we asked whether the family also supports you in a different way. So what they told, family is also supporting, but it comes at different cost. For example, family support reduces to 66 percentage when it comes to attending different conference or seminar at distance places. Then the family is like, okay, you don't go or you stay here, it's better not to go for that particular conference or seminar. Now, we also asked a question that how many of you are getting help or assistance or whatever, or like to be basically we asked whether the life partners are supporting in their life course, but actually the word supporting itself is not actually correct. We actually asked whether they are also participating in the household course in an equal manner. So they said that only 56% of women said that their life partners share household chores with them. But actually, this is the input from the survey. So 56% of them told that yes, they are sharing. But what is that share? So when we are doing the focal interviews, what we are getting is that they are saying that okay, they are helping, they are coming and they are doing something and then they are going. Or like somebody saying that okay, they're not coming to the kitchen, but they are doing some other helping. And then they're feeling that the women are feeling that okay, my life partner is helping us, so it's a kind of sharing of household chores. So that's the difference from the survey based answer and the focal interview based answer. So the focal interview based answer we are not discussing here because it's still ongoing. uh, we'll discuss this later, but this is the overall view from the marriage, partner and career section. Now, during PhD, what happened? So, we asked the respondents that whether they have found that women having children are facing more pressure than the others. So, 45.54% of them told that yes, they are facing more pressure or more difficulties in completing their research works. Now, we also asked restriction from my family affected my PhD or research, but very like restriction from family, it did not that much affect actually the career stage. But a few of them, for example, 3.96% of them told that yes, restriction from family affected their PhD. So similarly, different question. I'm not going through each and every questions. Some of the interesting things only I'm discussing. Now, what happens at the family and employer level? Now, pressure to get married during graduation, we already discussed. It varies across different communities and greatest among Muslim community. So we did an ANOVA to see whether the responses are different across communities. So we found that yes, it is different and it is high at Muslim community. Now, force of life partner and family to make changes in women's career. So that also different among different categories, and we found that it is greater among SC and ST communities. Now, people with bachelor's degree as their highest qualification. So they told that they had more financial struggles during their graduation compared to others. So this can be a reason why they didn't pursue their career for more qualifications or like master's degree or whatever. Now, one very interesting thing, women with lesser educational qualification believe, it's their belief, we asked, so that they're offered the job because as a woman, the employer can pay them less. But now there is a question whether it is a belief or this is actually happening. We don't know. We have to have a proper study on that. So now we also looked at the sector-wise difference. So we found that the tendency is greater in the private sector. So that is also a significant insightful result. Now, is there a rural-urban divide between the forces or restrictions or societal influence among the respondents? So we looked at this and we found that mothers among the respondents from semi-urban areas suffer more in completing their research works on time compared to the urban respondents or the rural respondents. Now, those who said that time and energy spent on household chores could be spent on career. So we asked a question in that way. Do you think that the time and energy you're spending on household chores can be spent on your career in a better and good manner? So semi-urban women recorded the highest response compared to the rural and urban sectors. Now, people from semi-urban and rural areas told that they would have chosen a faraway institute if they were given chances. So basically, it's either they didn't get a chance to go to a faraway institute, or they face some restriction to do that, or basically they don't have such kind of facilities in their surroundings. So then we also asked, sharing of household chores with partners is greatest is where. So urban women told that they are getting more support from their life partners compared to rural women or semi-urban. These results actually, these can be understood in a different level, so that we can actually think what will be the actual reasons behind these kind of responses from different sectors. Now at the end, what we did, we tried to model some of the factors, like as to model the career pathway or the pressure or the restriction or whatever influence the women are getting. So we looked at women with higher education. What are the molding factors or what are the influencing factors? So we did a multinomial regression to see this, and we found that the best predictive variables were favoritism towards the chemistry teacher in their school period, and then availability of a good chemistry lab at their school level, plus the financial capacity during graduation. So these three parameters or these three variables became the best predictive variables among the all variables we checked as a good predictor for women with higher education. Now, financial struggle during graduation was greatest among ST categories, followed by OBC. And we also found that around 50% have taken their career gaps. Okay, and that interesting part comes here. So they have taken a career gaps, fine, but why did they took the career gap? We asked that question, and 41% of the women told that it's because of maternity issues, and it's followed by family responsibilities, and it is followed by marriage. And the least, the 11% and 8%, you can see the reason is special coaching or for better career opportunities. So basically the career gap is not because their special coaching or for the betterment of their career opportunities, basically because of their maternity issues or family responsibilities, or other marriage related issues, or means basically the marriage, the time they are getting married, or the further some post marriage and pre marriage portions. Now the one of the thoughtful and thought provoking thing is that 60% of our respondents told that they have friends who dropped their career in chemistry. So that is a very large percentage, right? 60% of them are saying that they have friends. It's not like they have one friend. They have many friends who have dropped their career in chemistry. Why this is happening? So all these factors we have discussed in the result are affecting the women in chemical science, and that also in different way. It's not like one particular factor affecting all the women's in a same way. It acts in a differential manner based on the demographic parameters of the society they are living or the family they are growing up. Now we ask the participant, okay, so these are the issues you are facing, or these are the influences you are having, or these are the supporting factors you are getting. Now what are your suggestions to make the chemical science society more inclusive and more like kind of good place for women? So 33% of the respondents told that they need more social and family support to like pursue their dream career or dream career pathway. Now they told that creating awareness among girls about their rights, about the pulling factors, pushing factors, and
Is there a problem, Jathan?
Hello, sorry, some technical issues there.
Wait, your screen.
Wait, yeah, it got turned off. Now, can you see the screen?
Yes.
Sorry. This session, the awareness session, among their rights, pulling factors, and opportunities, it's very important. And as Professor Deepa was saying, all these motivating factors or inspiring factors, or how you should pursue your career, like, I mean, with not respect to others' comments or their thoughts or their opinions, basically. So that is one of the very important things suggested by most of the participants. And one other infrastructural thing, most of the respondents told that they need better laboratory environments in schools, graduates, and other different career stages. Plus, they told that even if they have their lab facilities and all, they should be allowed. They should be allowed to be in the lab for more time, and their hostel facilities should be near to the laboratory so that they can go and come from the laboratory uh, with not any other external factors or external societal influence or safety issues, all these things. So while discussing, these are like very small sentences, but these are very, I mean, this should be discussed in a very big canvas. But these are some of the suggestions as per. Now, creation of more opportunities and reservation for women was one of the very important suggestion by participants. And then they also told that financial assistance should be given to those who are deserving it. For example, we found that the financial struggles during the graduation period was mostly affected by uh, ST communities and OBC. So in that way, we should identify whom all are deserving it, and we should provide enough financial assistance in form of scholarship, fellowship, or any other modes. Now, the way forward is that, so these are the results from our preliminary analysis of the survey-based data. Now we are also conducting focal interviews to supplement this result and to know exactly what are the factors made our respondents to pursue the career or like to leave the career. For example, we are interviewing respondents who have dropped their career in chemistry, who are in some designations already. So we are trying to see what are the different factors they have faced along their career pathway. Now, after finishing this focal interview, we are planning for a panel discussion, including different key peoples in chemical science community, as well as the women community and the government also, to see what all things we can do in the future based on our preliminary or our basically the upcoming result. Now we are also planning to form a women in chemistry forum for Kerala to enhance the communication and enhance the collaboration between between the entities in chemical science society, chemical science community, especially the women's. And as part of this, we are also developing a mobile app called Chemicule, which can be used as a social media tool between researchers or faculties or students, so that they can communicate the news about conferences, events, workshops, job opportunities, new openings in their lab. All these things they can discuss. So that app also we are going to release. So basically and ultimately, using all these things, we are going to give a policy recommendation to the government, what all the factors are affecting the career pathway of women in Kerala, specifically for chemical science community, and to develop a framework for future of women in chemistry with more strategies of including inclusiveness. So this is it, and I would like to share a response from one of our respondents. She told that she really enjoyed answering our questionnaire. She dropped her first PhD for the sake of her family, but took a doctorate during her second attempt after qualifying UGC JRF at the age of 33. With two little kids in my hand, struggled a lot to build a career in chemistry, and she wishes smart, intelligent girls and deserving mothers should come up in their life and be rewarded for their great services to family and society. So by this, I conclude our presentation. We can discuss the questions we asked and the responses we got. And I would like to thank all of these people without which our work wouldn't have been possible. A lot of love to all these people, especially to the Royal Society of Chemistry, Inclusion and Diversity grants for funding and supporting our work. Thank you.
Thank you so much, Jithin. I'm sorry that you had to wrap up a little earlier because of our time constraint, and really we are running so short of time that I am afraid we can't get on with the discussion too much. So we'll directly open the Q&A session. Any quick questions, we'll be very glad to attend to. If not, I think we will share the email IDs of the speakers so that you can contact them, ma'am, with your permission, Prajval ma'am and Khushalani ma'am.
I think Prajval, Dr. Prajval has raised hand. So just take her question. She may be wanting to ask. She had raised her hand.
Ma'am, you can unmute and ask, ma'am.
Yeah, I had a question for Jitin actually. I was very heartened by the enormous effort and energy they've put into this. It's really amazing. So, one question I had is were you planning to interview people from different groups in the same situation? So, for instance, you've looked at women who are in research in chemistry. Are you planning to compare what results you might get by interviewing men and who are also in these same situations employed, and women who might have wanted to be employed but are not? And I just, I was curious because I don't know if you're aware of this Indian Academy of Sciences commissioned study by Kurup and others. So they found very interesting differences in the perceptions between the women who were employed in science and the women who had to drop out. So the reasons why there was a gender gap were very different as given by these two different groups. So because that will heavily affect your recommendations,
Yes, ma'am. Yes. So currently the focal interviews we are doing, actually we are interviewing these two kind of or two groups of people only. So those who are already in the career and those who are already dropped out from the career because of different reasons. And apart from that, the one suggestions you told to ask the or to interview the men and women in the same designation or the same profession, so that we had in mind, but most probably due to time constraints, we'll not be able to do in this time, but at least in the next stage of this study we'll definitely would like to do that.
Yeah, because it may not be that you will land up with a recommendation that says more financial support or something. Those suggestions go along the lines of fixing the women, whereas a lot of data is suggesting that we need to fix our institutions and we need to fix the biases within the institution. So, for example, a lot of women, at least in physics, have lost jobs simply because their spouse is employed in the same institution, and the institute has a hidden norm that they will not hire a spouse. They will not make it explicit, they will not make it transparent, but they will say it in the corridors and they will give some excuse in the committee minutes to implement it. So,
actually, there is a sole study on the topic which you are saying from MIT, like how this spouse and like basically the husband relationship affect their hiring and payment, all these things. Yeah, that's a nice
Right,
one.
but it happens if you quote MIT, people just brush this
Yeah.
aside, saying India is different. But
Yes.
India, in this particular case, India is not different. It's worse, if at all, it's worse. Yeah.
Yeah, true. Thank you, ma'am.
I hope, ma'am, that cleared your doubt. And I think we have another question I've received. Gitansh has a question open to all the speakers that what can we do at the ground level to address the issue of inclusion? Because yes, there are a lot of norms being made in workplaces, but and as we often see in the case of reservations, the mentality of people does not really change because some norms have been made. So what can really be done on from to change, so to say, the society's mindset?
Should I take that?
Sure, ma'am. And most welcome.
Yeah, so I mentioned this thing called the Hyderabad Charter for Gender Equity in Physics. It's something that is not only confined to physics. We, of course, looked at physics partly because I'm a physicist, and partly because the gender gap in physics is the worst. So it's like the worst manifestation of all the problems we're talking about. So one of the very strong recommendations we have is gender sensitization programs within institutions for everybody, mandatory, right from leadership downwards. So the idea is that, I mean, we're not saying that mindsets will change with just going through one program, but there is this understanding that one way to address bias is to make oneself aware of it. So gender sensitization programs, we believe, will at least raise some issues. I mean, many people have never thought about these things. Many people don't even think there is anything wrong, for example, in asking a potential candidate questions depending on what their gender is, rather than focusing on the merit of the job description that they are trying to hire. So whether it is men or women, I've had experience, scientists asking candidates what is their family situation, are they planning to get married, are they going to have a baby, and they will ask this only of the women. Similarly, when mentoring students, they will tell the men students, follow your passion, do all that. But to the women, they will say, you have to work very hard, you have to manage your family and your science, so very different advice given to men and women. And so I think gender sensitization programs can at least highlight that this is not okay, and at least get them to debate on these issues and maybe, change awareness.
Thank you so much, ma'am. Here, I myself have a question. Few months back, I saw in the news that in Nature Communications, a certain article had been published, which concluded that if your guide is a female scientist, it becomes detrimental to the career of a young researcher. It was pretty highly debated, and finally, if I remember correctly, it was retracted. The article was retracted, but the fact that something like this did reach the public through Nature Communications, what does that say about the direction we are heading towards?
So who do you want to answer? I mean, I already took the last question.
Ma'am, you can take it. I think anybody really, even Deepa ma'am is.
No, you can go ahead. Professor Shastri is far more better at making fantastic statements, so I will let her answer.
Well, so my reaction to that is, I mean, the most charitable, let's say, reaction to that is to say that they are confusing what is with what ought to be. So, there is the approach that you take, that you look at what is, and maybe their data did actually show that people who had women mentors were not advancing in their career. Now you have to look at why. And you cannot simply conclude that it is because they had the women mentors that they did not advance, right? Because the women mentors themselves will be targets of discrimination. So in a way, it is not surprising that, you know, I mentor somebody and then that somebody will be discriminated against simply because that somebody that I, as a mentor, mentored this person. So it's that is the most charitable. Eventually, you know, that paper got withdrawn. So, as you, rightly said, it was not eventually not seen as rigorous. Apart from the fact that, you know, it's very debilitating as well. So it also depends on what is your starting framework. I mean, are you going to say that we are all people and the scientific enterprise is open to all people? Not just, it is not actually, it is not, but it must be open to all people. So we have to make this distinction between what is and what ought to be. And when we suggest solutions to what is, those solutions cannot reinforce what ought to be. And in this particular case, they have to look at, you know, why are women discriminated? Because it is very, I mean, there's tons of data which shows us that women are discriminated at all levels, even up to very senior professor levels, you know. And there are expectations, you know, there are expectations of women. If you remember that slide that I showed, that cartoon that I showed in the end of my talk, there are expectations from behavioral expectations from women and how they believe, how they should behave in institutions. India March for Science had a series last year on invisible hurdles, and Shubha Tole from TIFR talked about how, you know, she's constantly asked to calm down, you know, in meetings. I mean, a person doing the same thing that she would have been doing, if that person were male, that person would be seen as very dynamic and how they have all these fantastic opinions. Whereas the moment you're a woman, you're not supposed to have these strong opinions, you're not supposed to express them. So the discrimination happens in so many layers and at so many levels. So the only feasible and tenable thing to do is to have a framework where you say this enterprise has to be welcoming of everybody. So if you're going to suggest any kind of intervention, whether it's seen as a band-aid or it's seen as a root cause addressal, it cannot reinforce what the root cause. So that's why I said in our charter, we say work-life balance policies cannot be patriarchal. If you look at the mobility scheme advertisement on the Department of Science and Technology website, it reeks of patriarchy. It's first of all only open to women, and it reeks of patriarchy. So those kind of things are not okay.
I will just, add to her answer, which is that, you see, a lot of the statements, or what a lot of the bias that is inherently there, comes from society. And I want, at least from my perspective, society is made up of both men and women. And that is why I think an active conversation and constant conversation to educate everybody is very important. You see, this bias, I'll tell you a bias, we talked about TIFR and Shubhatoli. I'll mention another thing about TIFR. We would, toilets in TIFR. You would think that they would be 50% would be female toilets and 50% would be male toilets. That is not the case. And there was an issue raised, which is we should have 50% female. So we should convert some of the male toilets to female toilets. The argument was made was, we don't have that many women in TIFR. So why should we have more female toilets? You understand? So it's a cyclical bias that is perpetuating itself, which is, yes, and they're absolutely true. The current status is we do not have 50% female ratio in TIFR. But is that allowed? Is that good? Should that be maintained? And shouldn't we actively participate in making sure that we have equal resources, and maybe those little things will help elevate the numbers? Okay, toilet is a horrible example to give, but you understand about the inherent bias. And it's about women also saying, well, why do we need more toilets, on campus? So so this is where I think it's very important when you say, but how do we deal with this, or how can this be happening? It's happening because everyone is participating in perpetuating a bias. In the data that the previous speaker was talking about, they kept saying, oh, the parents are worried, the parents are worried. Parents are both mother and father. If both of them are constantly worried, what is the girl to do? She has no example to live up to or look at and say, no, I can fight the system. When the parents themselves are saying, you cannot fight the system. Okay, and that is difficult. And like I said, I gave my example, which is sometimes you do not come from an environment which gives you a great deal of support. So this is where active conversations help in giving each other courage, in giving each other confidence to help change the system. The system is not going to change like this. All right, you, me, all of us actively participating, debating, and changing the mindset will evolve the system. You know, it's not about money. The government can pump in as much money as they want and as much as quota systems for females. That does not help respect. What we want is equal respect. We're willing to give equal respect, but we want equal respect. And that takes everybody to participate. If women are willing to take a back seat, willing to constantly take a back seat and say, okay, society wants me to do this, so I will do this, I will compromise, then you are contributing to perpetuating a bias as well. And I know it's difficult to swallow that sometimes, all right? And it's not easy, agreed. But all of us have to help with little steps. I'm not asking, I see it every day. And that is where everybody can take tangible things every day you do, which is also lead by example of how you behave, how you look at environment around you, and when do you notice that bias, okay? And say, no, this is wrong.
And by the way, on the subjects of toilets, they should just make them unisex toilets. I mean,
Yeah.
that helps. That helps make the institution more welcoming of all genders, and it also makes it welcoming for people with disabilities. It encompasses so many different things. So that's just the way to go. I mean, otherwise you're just perpetuating the subscription to the gender binary. And
there's so many prejudices we hold, and we think those prejudices are valid. Okay, so think about also the prejudices all of us have inherently, and you'll be surprised. Which is, as Professor Shastri said, women don't wear saris. The minute I will see a man in a sari, I think I will have a certain impression in my head, which may not be a good thing. All right.
Ma'am, Yagnit with us here has a question. Yagnit, you can unmute and ask.
Yeah, and I would like to ask Ma'am Prajval Shastri a question. What do you think the inclusion of women with disability, what is the future of them in astrophysics and astronomy in India and the entire world as a whole?
Okay, that's a difficult one. One thing I would like to say is that when we approach any kind of inclusion or fighting inequity, I think it is useful to take each dimension of inequity, like gender, for example, or disability, or any of these things, caste, as an example of how human beings can perpetuate discrimination, and how that can not just creep in, but how that can get entrenched even within the scientific enterprise, which has claims to being objective and all of those things. So each of these should be seen as examples, and therefore when we try to counter and when we try to work towards inclusion, we do need to work towards inclusion, diversity, and against discrimination on all these dimensions, whether it is caste or gender or sexual orientation or disability and so forth. So I think only then there will be some light at the end of the tunnel. And also, like the toilet example that I gave, for example, it's a small thing, but if it is addressed, then with the same policy, you're sort of addressing discrimination against two different groups that we don't normally think of as connected. As far as astrophysics is concerned, in India, there is very little work being done to enable and make the enterprise welcoming to people with disabilities. But there is a movement worldwide. There is our global society is called the International Astronomical Union, and they have given major funding to something called the Office of Astronomy for Development, whose mandate does include this, and it includes it does include both creating materials and evolving pedagogies and all of those things in order to make the profession inclusive for people with disabilities. We have a long way to go, doubtless, and astrophysics has always been seen as a very visual kind of subject, but there is work happening.
Thank you so much, ma'am.
Ma'am, I think we will take one last question. So we have a question here that says, it has become very fashionable these days to evoke the past and tradition to justify the actions of the present. So how does this trend affect the issue of progress through inclusion, especially in science? So, Prajval ma'am, Deepa ma'am. Yeah, a little controversial probably, but
Mr. Shastri, you can go first.
Please call me Prajval for starters. Well, it doesn't help. It only comes in the way. There's no two ways about it. We need to cast a vision for ourselves. There's a lot of merit in drawing upon any good aspects of our tradition, but we do need to sort of chart a vision for the scientific, for not just the scientific community, but for our citizenry. So this kind of a path that you mentioned has not helped us. For example, our society shows a huge science deficit, even with all the investment in science and technology, fairly generous investment, not as generous as we might like, but nevertheless pretty generous investment over the last 7 decades. And it has not resulted in any kind of elevation of scientific thinking. Science has always been a subject. It has never been a way of life. It has never been a way of thinking in our society by and large. So this path hasn't really helped us at all, and it has to do with not just it does not have to do with the amount of investment in science. Yeah, I mean, increasing that investment is not going to increase this. There's a lot of evidence that shows that. So, we do need to change that, and we do need to. I mean, India, I think I would say India is the only society where, for example, educated people, formally educated people, even with PhDs, will lead one life in their laboratories and a different kind of life outside of it. And without that kind of consistency, so for them science is not a way of life at all. And I have examples where people ask some scientists, how you are a scientist, how can you do such and such? For example, how can you imprison your pregnant daughter-in-law during an eclipse? And they will say, oh, that is our job, but this is life. So yeah,
I think it's how you are educated, how you look at your profession, how the idea of science for me has always been about looking forward, being inventive and discovering and charting a course that is based on valid principles with scientific data. So I think it's about, the question is, how do you look at your job, and how passionate, which is about, does it govern your way of life and your ability to be, forward thinking and progressive. And I think it's from person to person, but yeah, I think
Yes, but yeah, but I mean, I think there is also an obligation that when you are hired as a scientist, there ought to be an obligation that you subscribe to the scientific method.
absolutely.
It's not enough to just do that in your laboratory. I mean, you
So
do
this is where
subscribe
I
to the
think in the Indian system, people look at a job, whether they're a scientist or not, they just look at it as job in terms of financial compensation, and that I have a job and that is it. They do not see a scientific career as more of a, that it's a vocation. It's not just a 9 to 5 job. And it's about how you are helping society get better, how you're contributing to educating the next generation and moving our quality of life in a better direction. That obligation, I don't think a lot of people take that facet on as seriously. They just think of it as, how much money I will earn, how rich I can, financial gain is still one of the motivating factors for education in India, as opposed to other aspects. And I think there's a bigger question here that needs to be tackled, which is, and also, coming back to what Jitin was saying, I'll just say something from my opinion of the students, which is when females are taught, they're taught because they need to get educated. When boys are taught, they're taught because of a career they're going to make. Girls are not asked, what are you going to do with a PhD? They're just saying, oh, you got a PhD? Oh, you're studying a PhD? Fantastic. Whereas, are you going to use that PhD to make a better life for yourself, is a burden that is not put on the girls, okay? And I want everybody to think about this. Your education is about a career you want to make, a path you want to make, about something that you're going to do productively for the rest of your life. It doesn't have to be a PhD. You don't have to be a scientist. You can do anything. But the point is that you have a responsibility to this planet to contribute and make the environment around you better. All right, there's a reason you are living, there's a reason that you are on, and that obligation, same thing that Prajval is saying. So keep that in mind. There's a bigger picture here, and I do not think the girls are given that burden. One of the questions, Jitin, you can ask is, does your income run the house? Are you this, you might have a PhD in chemistry and your husband have a PhD in whatever, biology, but out of those two salaries, who runs the house? Who is the one who is more financially independent? Who looks at it as in terms of that they are the main carer for their environment, their society, their family? And that burden is not put on girls. So you want to talk about biases? There's an important bias to look at.
Yes, that's so true, ma'am. Yes, the financial independence is a very, I mean, we should have definitely included that component in our survey. But yeah, obviously in the next stage, we'll look at that particular aspect itself. Thank you.
Because a lot of confidence and success and feeling value comes from that.
Yes.
I think women need to appreciate that part. And that will help them move up in career. This leaky pipeline needs to be solved, and there's a lot of problems that contribute to that leaky pipeline.
I really wish this discussion could have extended because it really turned out so interesting. It's a shame that we did had so little time to carry this out finally because of all this time constraint throughout the sessions. But I guess we will have to stop here. Deepa ma'am, Prajval ma'am, Jithin, do you want me to share your email IDs just in case people have queries, further queries too?
That's fine. That's fine.
Yes, fine.
So I've posted the email IDs in the chat box. If anyone has further questions, because we really could not carry on the session as long as we wished we could, please contact them. So here I would like to hand over to Pranav to propose the vote of thanks. And one point I would like to mention before handing over is that there is a feedback form for the session, which will shortly be, so it has been posted on the chat box. I would request everyone to give their feedback, and also it is essential for getting the participation certificate. So yes, over to you, Pranav.
So, after a wonderful evening of discussions and presentations, on behalf of the Xavier's Association of Chemistry, I deem it as a great honor to propose the vote of thanks for all those who have helped us in making this webinar on inclusion, a cornerstone of scientific progress, such a resounding success. First of all, I'd like to express our heartfelt gratitude to Professor Prajval Shastri and Professor Deepa Khushalani for sharing their vast knowledge, experience, and insight with us. Indeed, your talks have been no less than eye openers and have surely inspired all of us today deeply. Thank you, Professor Shastri and Professor Khushalani, for the engaging, thought-provoking addresses and the amazing presentations. I would also like to extend our appreciation to our presenters of the day, Mr. Vijayan, Miss Asmabi, Mr. Jasil, Miss Anu, Miss Hanan, and Mr. Srinath. It is wonderful to see budding researchers addressing the issue of inclusion with such caliber and finesse. The scientific community desperately needs more enthusiasts like you all. I would also like to take this moment to thank our head of department, Mr. Marzban Kotwal, and all our professors for their continued support and guidance. I would like to express my gratitude to all the coordinators and volunteers for making this event a great success. And lastly, to the wonderful and cooperative audience without whom this webinar would have been merely a dream. Thank you all.
Yeah, thanks everyone. Bonobiti, you can make the final announcement.
Yes, thank you, ma'am. Thank you, everybody. And of course, we have day 2 of ALCHEMIA on Monday, but that is only for the games and events. So I don't think the professors will be interested. But the rest of the audience, the students here especially, please make sure to join in. So I think that will be all. Thank you so much. Thank you really a lot.
Very well